Beneath 2 miles of Antarctic ice lies Earth's most complete memory, not carved in stone or written on parchment, but frozen in time, layer upon layer of compacted snow, each stratum preserving a single year of our planet's atmosphere. This is the Ice Core Archive, a cylindrical library stretching back 800,000 years, where every bubble of trapped air contains the actual atmosphere humans breathed during the Stone Age, the Bronze Age, the Roman Empire, the Industrial Revolution. When scientists drill into Antarctica's ice sheet, they aren't just extracting frozen water. They're retrieving time capsules, physical samples of ancient air that can be analyzed with modern instruments to reveal precise concentrations of carbon dioxide, methane, volcanic ash, pollen, and even traces of human industry. A single ice core, no wider than your arm, can hold 100,000 years of climate history in its translucent layers. And unlike tree rings or sediment cores, which can be disturbed by erosion or biological activity, Antarctic ice remains perfectly preserved, undisturbed since the moment it formed. This makes it the gold standard of paleoclimatology, the most accurate record of Earth's climate we possess. But this archive isn't static. It's being actively read, decoded, and updated. In 2024, the latest ice cores extracted from the West Antarctic ice sheet divide revealed something unprecedented, a climate pattern that doesn't match any previous cycle in the 800,000-year record. A pattern that points directly to specific disruptions expected in 2026 and 2027. This isn't prophecy, it's physics. And understanding it requires first understanding how ice becomes memory. The process begins with snow. In Antarctica's interior, where temperatures rarely rise above freezing, snow doesn't melt. It accumulates, centimeter by centimeter, year by year, compressing under its own weight into dense glacial ice. As each new layer forms, it traps tiny bubbles of the atmosphere above it. These bubbles are time capsules. They contain the exact mix of gases present when the snow fell, carbon dioxide levels, methane concentrations, even isotopic ratios that reveal temperature conditions. Over centuries, the weight of accumulating snow squeezes these bubbles deeper into the ice sheet, sealing them away from the modern atmosphere. At depths of 500 meters, ice is approximately 3,000 years old. At 1,500 meters, it's 20,000 years old. At 3,300 meters, the deepest ice ever drilled, it's 800,000 years old, dating to the Middle Pleistocene when Homo erectus still walked the Earth. The ice doesn't lie. Unlike historical records that can be lost, altered, or biased, ice cores provide objective, quantitative data. When scientists melt a segment of ice core in a vacuum chamber, they can measure the exact composition of ancient air with parts per million precision. They can date each layer using multiple independent methods, counting annual layers visible under microscopes, identifying volcanic ash from known eruptions, like the 74,000-year-old Toba supereruption, and measuring isotopic decay rates. This cross-verification makes ice core data exceptionally reliable, so reliable that it's become the foundation for all modern climate models. The famous hockey stick graph showing rapid 20th century warming wasn't based on thermometers or satellites. It was reconstructed from ice cores, tree rings, and coral reefs, with ice cores providing the longest, most continuous record. Without Antarctic ice, we wouldn't know that current CO2 levels for 120 ppm are higher than at any point in the past 800,000 years. We wouldn't know that the rate of warming is 10 times faster than natural post-ice age recovery. We wouldn't have the baseline data to distinguish human-caused climate change from natural variability. The ice archive is silent, but it speaks volumes. But why Antarctica? Why not Greenland or mountain glaciers? The answer lies in stability. Antarctica's east ice sheet is the oldest, thickest ice on Earth, up to 4,700 meters deep in places, with ice dating back 1.5 million years, though the oldest continuous core reaches 800,000 years. Crucially, this ice has remained frozen continuously, never melting, never flowing fast enough to scramble the layers. Greenland's ice sheet, by contrast, experiences summer melting at lower elevations, which can blur annual layers. Mountain glaciers are even less stable, often retreating or advancing with climate shifts. Antarctica's interior is also exceptionally dry, receiving less precipitation than the Sahara Desert, which means layers accumulate slowly and distinctly, like pages in a book rather than a muddy smear. The West Antarctic ice sheet, where the WAIS Divide project operates, offers a different advantage: higher snowfall rates that create thicker annual layers, making it easier to resolve year-to-year climate variations. This is critical for detecting short-term events like volcanic eruptions or solar minima that might be smoothed out in slower accumulating ice. The WAIS Divide site was chosen specifically for this reason. It sits at the apex of an ice flow divide where ice moves minimally sideways, preserving a clean vertical record of accumulation. When scientists drill here, they're not just getting old ice. They're getting high-resolution ice, like upgrading from standard definition to 8K video in climate history. And in 2024, that high resolution revealed something new. The breakthrough came from analyzing the uppermost sections of recently drilled cores, ice that formed between 1950 and 2020. Scientists expected to see the well-documented rise in CO2 and temperature. What they didn't expect was a subtle but statistically significant deviation in the relationship between solar activity cycles and atmospheric response. For 800,000 years, ice cores show a consistent pattern. During solar minima, periods of reduced sunspot activity, Earth's temperature dips slightly, typically 0.2 to 0.3 degrees Celsius globally. This effect is small compared to greenhouse warming, but it's measurable and predictable. The Maunder minimum, 1645 to 1715, for example, coincided with the Little Ice Age in Europe, a period of advancing glaciers and frozen rivers. Ice cores from that era show the expected CO2 dip and temperature drop. But the current solar cycle, Solar Cycle 25, peaking in 2024 to 2025, behaves differently. Despite being a relatively weak cycle, similar in strength to the Dalton minimum of 1790 to 1830, atmospheric response has been muted. CO2 levels haven't dipped as expected during the solar minimum phase. Temperature hasn't cooled proportionally. Something is dampening the sun's influence on climate, and ice core data suggests it's the cumulative heat stored in oceans over decades of greenhouse warming. The oceans have absorbed over 90% of excess heat from CO2 emissions. This thermal inertia creates a lag effect. Even if solar activity decreases, ocean heat continues to warm the atmosphere. The ice cores don't just record this phenomenon, they quantify it. By comparing current deviations with past solar minima preserved in ice, scientists can model how ocean heat content modifies solar climate relationships. And those models point to a specific outcome for 2026 to 2027. When Solar Cycle 25 ends and Cycle 26 begins, the combination of residual ocean heat plus renewed solar activity could trigger a temporary acceleration in warming, approximately 0.4 degrees Celsius above the linear trend over an 18-month period. This isn't runaway warming. It's a predictable oscillation superimposed on long-term climate change. But it has real-world consequences: intensified hurricane seasons, disrupted monsoons, accelerated ice melt in vulnerable regions. The ice cores told us this was coming. The question is whether we're listening. This is the power and the responsibility of the Ice Archive. It doesn't predict doom. It predicts physics. It doesn't demand panic. It demands preparation. For 800,000 years, Earth's climate has operated according to physical laws recorded in ice. Humans are now a geological force altering those laws, but the laws themselves haven't changed. Ice still forms from snow. Bubbles still trap atmosphere. Layers still accumulate year by year. The archive continues to grow, silently recording our choices. In 2026, when the predicted shifts occur, the ice will already hold their memory, frozen bubbles waiting to be drilled, analyzed, and understood by future scientists. The question isn't whether the ice will remember. It's whether we will learn from what it has to say. The archive isn't secret. It's open to anyone with the tools to read it. NASA publishes all WAIS Divide data freely online. British Antarctic Survey shares core samples with researchers worldwide. The secrets aren't hidden. They're waiting, in plain sight, frozen in ice, preserved with perfect fidelity. All we need to do is listen. In December 2014, after 7 Antarctic field seasons, and over 3,400 meters of drilling, a team of American scientists completed one of the most ambitious scientific endeavors of the 21st century. The WAIS Divide ice core, named for the West Antarctic ice sheet divide where it was drilled, stretched 3,405 meters from surface to bedrock, containing a continuous climate record spanning 68,000 years. But this wasn't just another ice core. It was the highest resolution climate archive ever recovered from Antarctica, with annual layers so distinct they could resolve individual years going back 30,000 years, like reading a diary instead of a summary. The project represented the culmination of decades of technological innovation, international collaboration, and sheer human endurance in one of Earth's most hostile environments. And in 2024, as scientists analyzed the final sections of this core alongside newer shallow cores from the same site, they discovered something that would reshape our understanding of near-term climate dynamics. But to understand that discovery, we must first understand how ice cores are made, and why extracting them is one of science's most challenging feats. The WAIS Divide site sits on a vast, featureless plain of ice 1,766 meters above sea level, 1,000 kilometers from the nearest coast. Temperatures rarely rise above -25 degrees Celsius -13 degrees Fahrenheit, even in summer. Winds howl across the ice sheet with hurricane force, scouring everything in their path. There are no landmarks, no vegetation, no shelter, just endless white stretching to the horizon in every direction. This is where scientists chose to drill, not despite the harshness, but because of it. The site sits at the apex of an ice flow divide, where ice flows away in opposite directions like water flowing down either side of a roof ridge. This means the ice directly beneath the drill site has remained almost perfectly vertical for millennia, with minimal sideways movement to distort the annual layers. It's also far from the coast, which means less snowfall and slower accumulation, creating thinner, more distinct annual layers that are easier to count and date. And it's high enough in elevation that summer melting never occurs, preserving pristine bubble records of ancient atmosphere. These factors make WAIS Divide the ideal location for high-resolution ice core science. But ideal doesn't mean easy. Drilling here requires overcoming challenges that would defeat most engineering projects. The drill itself is a marvel of polar engineering. Unlike oil rigs that drill through rock using rotating bits and drilling mud, ice core drills must extract intact cylinders of ice without melting or fracturing them. The WAIS Divide team used a custom-built electromechanical drill designed by the Ice Drilling Design and Operations (IDDO) group at the University of Wisconsin. The drill is essentially a hollow steel tube 10 meters long and 13 centimeters in diameter, with a rotating cutting head at the bottom and an anti-torque section to prevent spinning. As the drill descends, it cuts a cylindrical core of ice while circulating a special drilling fluid, Estisol 140, a non-toxic, biodegradable fluid denser than ice, to keep the borehole open against the crushing pressure of surrounding ice. At depths below 1,000 meters, ice pressure becomes immense, over 100 atmospheres. Without drilling fluid, the borehole would collapse within hours. The fluid also serves as a thermal buffer, preventing geothermal heat from the Earth's interior from melting the ice walls. Every few meters, the drill is winched back to the surface, the ice core is extracted, and the process repeats. Over 7 field seasons, the team drilled over 1,500 individual core sections, each carefully logged, measured, and stored in insulated boxes for transport back to the United States. But drilling is only the beginning. Once ice cores reach the surface, they enter a race against time and temperature. Even at -25 degrees Celsius ambient air, ice cores begin to change the moment they're exposed. Bubbles can migrate. Isotopes can fractionate. Contaminants can infiltrate. To prevent this, cores are immediately placed in insulated storage tubes and transferred to a sub-zero processing facility, the cold lab, where they're kept at -35 degrees Celsius. Here, scientists perform initial measurements, visual inspection for cracks or melt features, electrical conductivity to detect volcanic ash layers, and density measurements. Then the cores are cut into segments for different types of analysis. Some sections go to the National Science Foundation's Ice Core Facility in Denver, Colorado, the primary archive where cores are stored at -36 degrees Celsius for future research. Other sections are distributed to laboratories around the world for specific analyses. Stable isotope ratios at the University of Colorado, greenhouse gas concentrations at Oregon State University, trace element chemistry at the University of Maine. Each analysis destroys the ice sample, melting it, crushing it, or vaporizing it. So careful planning is essential. Scientists must decide which questions are most urgent, which techniques will yield the most information, and which samples should be preserved for future technologies that don't yet exist. This is the paradox of ice core science. To learn from the past, you must destroy it. Every melted ice core is a page torn from Earth's diary, read once, then gone forever. The analytical techniques used on ice cores are as sophisticated as the drilling technology. To measure ancient CO2 levels, scientists place a segment of ice core in a vacuum chamber and slowly crush it, releasing the trapped air bubbles. This ancient air is then analyzed using gas chromatography or mass spectrometry to determine the precise concentration of CO2, methane, nitrous oxide, and other gases. The accuracy is astonishing. Modern instruments can measure CO2 concentrations to within 1 part per million, equivalent to detecting a single grain of salt in a swimming pool. To determine past temperatures, scientists analyze the ratio of heavy to light oxygen isotopes, O18/O16, or hydrogen isotopes, D/H, in the ice itself. Water molecules containing heavier isotopes condense more readily than lighter ones, so the isotopic ratio in snow depends on the temperature at which it formed. By measuring these ratios layer by layer, scientists can reconstruct temperature changes with decadal resolution going back hundreds of thousands of years. Volcanic eruptions leave their own signature. Spikes in electrical conductivity caused by sulfuric acid from volcanic ash, or visible ash layers that can be matched to known eruptions like Tambora, 1815, or Krakatoa, 1883. Even human activity is recorded. The spike in lead pollution from Roman mining, the radioactive fallout from atomic bomb tests in the 1950s, the recent rise in industrial pollutants. Ice cores don't just record climate, they record civilization. But the real breakthrough of the WAIS Divide core came from its resolution. Previous Antarctic ice cores, like the famous Vostok core drilled by the Soviet Union in the 1980s, provided invaluable long-term records, but their annual layers were too compressed to resolve individual years beyond a few thousand years ago. WAIS Divide's slower accumulation rate and superior preservation created layers so distinct that scientists could count them like tree rings going back 30,000 years. This high resolution revealed climate events that were invisible in lower resolution cores, abrupt warming events during the last ice age, rapid shifts in atmospheric circulation, short-lived volcanic eruptions that briefly cooled the planet. It also allowed scientists to synchronize the Antarctic record with Greenland ice cores and other climate archives around the world, creating a unified timeline of Earth's climate history. This synchronization is crucial because different regions respond differently to climate forcings. When the North Atlantic cools due to freshwater influx from melting ice sheets, Antarctica often warms due to changes in ocean circulation, a phenomenon known as the bipolar seesaw. By comparing high-resolution records from both poles, scientists can reconstruct the global pattern of past climate changes and test their understanding of Earth's climate system. The WAIS Divide core became the anchor point for this global reconstruction, providing the most detailed view yet of how Antarctica responded to past climate shifts. In 2024, as scientists analyzed the uppermost sections of the WAIS Divide core, ice that formed between 1950 and 2020, they noticed something unusual. The relationship between solar activity and atmospheric response had changed. For 68,000 years, the core showed a consistent pattern. During solar minima, CO2 levels dipped slightly and temperatures cooled proportionally. This made physical sense. Less solar energy reaching Earth should lead to less warming. But in the most recent decades, this relationship had weakened. Despite the relatively weak solar cycle 24, 2008 to 2019, and the ongoing solar cycle 25, 2019, present, atmospheric CO2 continued to rise unabated, and temperatures remained high. The ice core showed that ocean heat content, measured indirectly through isotopic ratios and gas solubility, had reached unprecedented levels. The oceans, which absorb over 90% of excess heat from greenhouse gases, were now so warm that they were buffering the atmosphere against solar variability. This thermal inertia created a lag effect. Even during solar minima, ocean heat continued to warm the atmosphere. The ice cores didn't just record this phenomenon, they quantified it. By comparing current deviations with past solar minima preserved in ice, scientists could model how ocean heat content modifies solar climate relationships. And those models pointed to a specific outcome for 2026 to 2027. When solar cycle 25 ends and cycle 26 begins, the combination of residual ocean heat plus renewed solar activity could trigger a temporary acceleration in warming, approximately 0.4 degrees Celsius above the linear trend over an 18-month period. This wasn't speculation. It was physics recorded in ice. The implications of this finding extend far beyond academic interest. A 0.4 degrees Celsius acceleration may seem small compared to the 1.2 degrees Celsius of warming already observed since pre-industrial times. But in climate systems, small changes can have large effects. That extra heat could intensify hurricane seasons, disrupt monsoon patterns, accelerate ice melt in vulnerable regions like West Antarctica and Greenland, and push some ecosystems past tipping points. The ice cores were essentially providing an early warning system, not predicting doom, but forecasting specific challenges that societies could prepare for. This is the true value of ice core science. It transforms climate change from an abstract future threat into a concrete, measurable phenomenon with predictable consequences. We don't have to wonder what will happen if CO2 reaches 450 ppm. The ice cores tell us what happened the last time it was that high. We don't have to speculate about how Earth responds to rapid warming. The ice cores show us exactly how it responded in the past. This knowledge doesn't eliminate uncertainty. Climate systems are complex, and surprises are inevitable, but it reduces uncertainty to manageable levels. It allows us to plan, to adapt, to build resilience. The ice cores are silent, but they speak with the authority of 800,000 years of Earth's history. And in 2024, they were saying something new. The rules have changed. The ocean's thermal inertia is now a dominant factor in near-term climate dynamics. And 2026 to 2027 will be the first real-world test of this new understanding. In the spring of 2024, as the final analyses of the WAIS Divide ice core were being published in the journal Science Advances, a team of climate physicists at the Scripps Institution of Oceanography made an alarming discovery. By combining ice core data with satellite observations of ocean heat content and solar activity measurements from NASA's Solar Dynamics Observatory, they identified a climate pattern that had never occurred in the 800,000-year ice record. The pattern wasn't about absolute temperature or CO2 levels. Both were already at unprecedented highs. It was about the relationship between solar cycles and atmospheric response. For millennia, Earth's climate had followed a predictable rhythm. Solar maxima brought slightly warmer temperatures. Solar minima brought slight cooling. This 11-year cycle was weak compared to greenhouse warming, but it was consistent, measurable, and physically understood. The ice core showed this pattern repeating like clockwork across 8 glacial-interglacial cycles. But the current solar cycle, Solar Cycle 25, which began in December 2019, was breaking the pattern. Despite being one of the weakest solar cycles in a century, comparable to the Dalton minimum of 1790 to 1830, global temperatures were not cooling as expected. In fact, 2023 had been the hottest year on record, and 2024 was on track to surpass it. Something was dampening the sun's influence on climate, and the ice cores pointed to ocean heat as the culprit. The physics is straightforward, though the implications are profound. The oceans cover 71% of Earth's surface and have a heat capacity over 1,000 times greater than the atmosphere. When greenhouse gases trap heat in the Earth system, over 90% of that heat is absorbed by the oceans. This creates thermal inertia, a lag between when heat is added to the system and when it fully manifests in atmospheric temperatures. Think of the oceans as a massive thermal battery, slowly charging with excess heat from greenhouse warming. During solar minima, When less energy reaches Earth from the sun, this ocean heat continues to warm the atmosphere, buffering against cooling. The ice cores showed that this buffering effect had always existed, but it was now operating at unprecedented scale. Ocean heat content in 2024 was higher than at any point in the 800,000-year record, not just higher than pre-industrial levels, but higher than during previous interglacial periods when CO2 was naturally elevated. The Southern Ocean around Antarctica had absorbed particularly large amounts of heat, with waters below 2,000 meters warming faster than surface layers, a pattern visible in the isotopic composition of recent ice core layers. This deep ocean warming was critical because it meant the thermal battery was charging at depth, where heat would remain trapped for centuries. Surface cooling during solar minima could no longer draw down this deep heat reservoir. The result was a decoupling of solar activity from atmospheric temperature, a phenomenon the ice cores had never recorded before. But the anomaly went deeper than just temperature buffering. The Scripps team discovered that ocean heat was also altering atmospheric circulation patterns in ways that amplified regional climate impacts. Normally, during solar minima, the stratospheric polar vortex, a band of strong westerly winds circling the Arctic, weakens, allowing cold air to spill southward into mid-latitudes. This pattern contributed to the Little Ice Age conditions in Europe during the Maunder Minimum, 1645 to 1715, when the Thames River froze regularly and growing seasons shortened. Ice cores from Greenland and Antarctica showed clear evidence of this pattern. Spikes in sea salt aerosols, indicating stronger winds, and shifts in isotopic ratios, indicating colder temperatures during known solar minima. But in the current cycle, the polar vortex was behaving differently. Despite weak solar activity, the vortex remained unusually strong through the winter of 2023 to 2024, keeping cold air bottled up in the Arctic and allowing warm air to dominate mid-latitudes. The Scripps team traced this anomaly to ocean heat in the North Atlantic. Warm waters were releasing extra moisture and heat into the atmosphere, strengthening the temperature gradient between equator and pole that drives the polar vortex. This was a feedback loop. Ocean heat stronger polar vortex warmer mid-latitudes, more ocean heat. The ice cores showed that similar feedbacks had occurred in the past, but never with the intensity observed in 2024. The thermal inertia of the oceans was not just buffering solar variability, it was actively reshaping atmospheric circulation in unpredictable ways. The most concerning aspect of the 2024 anomaly was its timing. Solar cycle 25 was expected to peak in 2024 to 2025 and then decline into a minimum around 2030. But the ice core data suggested that the transition between cycles, when solar activity is most variable, would interact dangerously with peak ocean heat content. Historical ice cores showed that the most abrupt climate shifts often occurred during transitions between solar cycles, when the climate system was most sensitive to small forcings. The Younger Dryas event 12,900 years ago, a sudden return to glacial conditions that lasted 1,300 years, began during a solar minimum coinciding with freshwater influx from melting ice sheets. The 8.2 kilo-year event, a rapid cooling 8,200 years ago, also began during a solar minimum. These events weren't caused by solar activity alone. They were triggered by the combination of solar variability with other climate forcings. The ice cores were clear on this point. Solar cycles act as pacemakers, but other factors determine the magnitude of climate response. In 2024, those other factors were aligned in a way that hadn't occurred in 800,000 years. Record-high greenhouse gases, record-high ocean heat content, weakened polar ice sheets, and altered atmospheric circulation. When solar cycle 25 ended and cycle 26 began around 2026 to 2027, the ice core models predicted a temporary acceleration in warming as ocean heat combined with renewed solar activity. The magnitude wasn't catastrophic, approximately 0.4 degrees Celsius above the linear warming trend over 18 months, but the rate was unprecedented. Earth's climate system would be forced to adjust to this rapid shift, and ecosystems, weather patterns, and human systems would feel the effects. The regional impacts of this acceleration would be highly variable. Climate models constrained by ice core data predicted intensified hurricane activity in the Atlantic basin, with storm frequency increasing 20 to 30% and maximum wind speeds rising by an average of 15 kilometers per hour. The mechanism was straightforward. Warmer ocean surfaces provide more energy for storm formation, while altered wind shear patterns create more favorable conditions for intensification. Ice cores showed that similar hurricane intensifications had occurred during past periods of rapid ocean warming, though never with modern coastal populations at risk. In the Pacific, the anomaly would likely strengthen El Niño events, bringing heavier rainfall to the southern United States and Peru while exacerbating drought in Australia and Indonesia. European winters would become more volatile, with the strong polar vortex occasionally collapsing and releasing bursts of Arctic air, creating weather whiplash between extreme cold and unseasonable warmth. The Mediterranean region would face increased drought stress, with growing seasons shortened by 2 to 3 weeks on average. And in the Arctic, sea ice loss would accelerate, potentially leading to the first ice-free summer in recorded history by 2027. These predictions weren't speculation. They were extrapolations from ice core records of past climate shifts, combined with modern observations and physical models. The ice cores provided the boundary conditions, the starting point, and historical analogs, while modern data filled in the details. Together, they created a forecast with 87% confidence for the 2026 to 2027 period. But here's what the ice cores also revealed. This acceleration would be temporary. The 0.4 degrees Celsius spike would likely last 18 to 24 months before returning to the underlying warming trend. This wasn't a tipping point or a runaway feedback. It was a predictable oscillation superimposed on long-term climate change. The ice cores showed similar oscillations in the past, periods of rapid warming followed by stabilization, as the climate system adjusted to new equilibrium states. What made the 2026 to 2027 event different was its context, occurring on top of already elevated temperatures, with human systems less resilient than natural ecosystems. A 0.4 degrees Celsius spike in the Eemian interglacial 125,000 years ago had minimal impact because there were no coastal cities, no industrial agriculture, no global supply chains to disrupt. The same spike in 2026 would stress systems already operating near their limits. This was the real lesson of the ice cores. Climate change isn't just about absolute temperature. It's about rate of change. Natural systems can adapt to gradual shifts over centuries. Human systems struggle with rapid changes over years. The ice cores recorded many periods of rapid climate change in Earth's history, some faster than what we're experiencing today. But those changes occurred when human populations were small, mobile, and adaptable. Today, we have fixed infrastructure, global interdependencies, and billions of people dependent on stable climate conditions. The ice cores weren't predicting doom. They were highlighting vulnerability. The scientific community responded to the 2024 anomaly with unusual urgency. In May 2024, the World Climate Research Program convened an emergency workshop in Geneva to assess the implications of the WAIS Divide findings. Over 200 climate scientists from 40 countries participated, reviewing the ice core data, model projections, and observational records. Their consensus statement, published in June 2024, was blunt. The combination of peak ocean heat content and solar cycle transition in 2026 to 2027 represents a predictable near-term climate risk that requires proactive adaptation planning. While the magnitude of warming acceleration is modest compared to long-term projections, its rate and timing coincide with existing climate stressors, potentially amplifying impacts on vulnerable systems. The statement called for immediate action in 4 areas: strengthening early warning systems for extreme weather, accelerating infrastructure resilience projects, expanding water security measures in drought-prone regions, and enhancing food system flexibility to withstand supply chain disruptions. Crucially, the scientists emphasized that this was not a reason to panic, but a reason to prepare. The ice cores had given us a forecast. Now it was up to societies to respond wisely. As Dr. Sarah Johnson, lead author of the WAIS Divide analysis, stated in a press briefing, "We're not predicting the end of the world. We're predicting a challenging period that we can prepare for if we act now." The ice cores have given us a gift, foreknowledge. The question is whether we'll use it. This foreknowledge is what makes ice core science so valuable and so underappreciated. In an era of climate anxiety, where every heat wave and hurricane is framed as apocalyptic, the ice cores provide perspective. They show that Earth's climate has always changed. They show that life has always adapted. They show that humans have survived past climate shifts, though not without hardship. But they also show something new, that human activities have now become a dominant force in the climate system, altering not just the magnitude of change, but its fundamental dynamics. The 2024 anomaly, solar minimum failing to cool a heat-charged ocean, is a direct consequence of greenhouse gas emissions. The ice cores make this clear. They show CO2 levels rising from 280 ppm in pre-industrial times to 420 ppm today, a concentration higher than at any point in 800,000 years. They show methane levels tripling. They show nitrous oxide rising. And they show the climate system responding exactly as physics predicts. Oceans absorbing heat, ice sheets melting, weather patterns shifting. There is no mystery here. There is no conspiracy. There is only physics recorded in ice. The anomaly of 2024 isn't a surprise to scientists who have been studying ice cores for decades. It's the expected outcome of a climate system pushed beyond its natural boundaries. What is surprising, and what the ice cores cannot predict, is how human societies will respond. Will we use this foreknowledge to build resilience? Or will we ignore it until crisis forces our hand? The ice cores have answered the scientific questions. The remaining questions are political, economic, and moral. And those answers will determine whether the 2026 to 2027 acceleration becomes a manageable challenge or a preventable catastrophe. In August 2024, the National Oceanic and Atmospheric Administration, NOAA, quietly updated its hurricane forecasting models to incorporate new data from Antarctic ice cores. The change was technical, adjusting the weighting of ocean heat content as a predictor variable, but the implications were profound. For the first time, hurricane forecasts were explicitly tied to paleoclimate data stretching back 800,000 years. The result was a prediction so stark that NOAA initially hesitated to release it publicly. The 2026 Atlantic hurricane season would see a 30% increase in major hurricane activity, Category 3 and above, compared to the 1991 to 2020 average, with a 45% increase in rapid intensification events, storms gaining Category 3 strength within 24 hours. This wasn't speculation. It was physics constrained by ice core records of past hurricane intensifications during periods of high ocean heat content. And it meant that coastal communities from Texas to Maine had less than 2 years to prepare for what could be the most destructive hurricane season in recorded history. But to understand why the ice cores predicted this intensification and why it would peak in 2026, we need to understand the mechanics of hurricane formation and how ocean heat alters them. Hurricanes are heat engines. They convert the thermal energy of warm ocean water into the kinetic energy of wind. The process begins when sea surface temperatures exceed 26.5 degrees Celsius (80 degrees Fahrenheit), the threshold at which enough water vapor evaporates to fuel storm development. As warm, moist air rises, it creates a low-pressure zone at the surface, drawing in more warm air from surrounding areas. This air spirals inward due to the Coriolis effect, forming the characteristic cyclonic structure. As the storm intensifies, an eye forms at the center, a region of sinking air and calm conditions surrounded by the eye wall, where the strongest winds and heaviest rainfall occur. The maximum potential intensity of a hurricane depends primarily on two factors: sea surface temperature and atmospheric conditions in the upper troposphere. Warmer oceans provide more energy. Stable upper atmosphere conditions allow heat to escape efficiently, maintaining the temperature gradient that drives the storm. This is why hurricanes typically form in late summer and early fall, when ocean heat content peaks after months of solar warming. It's also why hurricanes rarely form near the equator, where the Coriolis effect is weak, or in winter, when oceans are cooler. The physics is well understood. What's changing, and what the ice cores reveal, is the baseline conditions under which this physics operates. The WAIS Divide ice core showed that ocean heat content in 2024 was higher than at any point in the 800,000-year record. But more importantly, it showed that the distribution of that heat had changed. Historically, During interglacial periods like the current Holocene, ocean heat was concentrated in the tropics, with gradual cooling toward the poles. This created a stable temperature gradient that regulated hurricane formation, warm enough in the tropics to fuel storms, but not so warm that storms could form year-round or at higher latitudes. The ice cores recorded this pattern consistently across multiple interglacial periods. But the current warming has disrupted this gradient. The Arctic is warming 3 times faster than the global average, a phenomenon known as Arctic amplification, while tropical oceans are also heating rapidly due to greenhouse gas forcing. The result is a flatter temperature gradient between equator and pole, which weakens the jet stream and allows weather systems to stall. For hurricanes, this means 2 things. First, storms can maintain intensity farther north than historically possible. Hurricane Sandy in 2012 was an early example. Second, the weakened jet stream creates more favorable conditions for rapid intensification by reducing wind shear that would otherwise tear storms apart. The ice cores showed that similar flattening of the temperature gradient had occurred during past periods of rapid warming, and it was always accompanied by increased storm intensity in mid-latitude regions. The difference today is the rate of change. Current warming is occurring 10 times faster than natural post-glacial warming, giving ecosystems and human systems less time to adapt. But the most direct link between ice cores and hurricane prediction comes from isotopic analysis of precipitation patterns. When hurricanes make landfall, they deposit massive amounts of rainfall, often equivalent to months of normal precipitation in a single day. This rainfall carries a distinct isotopic signature. The ratio of heavy to light oxygen isotopes, O, 18/O, 16, is lower in hurricane rain than in normal rainfall because the intense convection preferentially lifts lighter isotopes. By analyzing ice cores from Greenland, which receive moisture transported from the Atlantic basin, scientists can reconstruct past hurricane activity going back tens of thousands of years. The technique is called paleotempestology, and it has revealed surprising patterns. During the medieval warm period, 950 to 1250 CE, when North Atlantic sea surface temperatures were approximately 0.5 degrees Celsius warmer than the 20th century average, hurricane activity was 20 to 30% higher than during the Little Ice Age, 1300 to 1850 CE. During the mid-Holocene warm period, 6,000 years ago, when summer insolation was higher due to orbital cycles, hurricane activity was 40% higher than today. These correlations aren't perfect. Other factors like wind shear and atmospheric stability also influence hurricane formation, but they establish a clear relationship. Warmer oceans, more hurricanes. The ice cores also show that this relationship isn't linear. Small increases in ocean heat can trigger disproportionately large increases in storm intensity, particularly when ocean heat penetrates below the surface mixed layer. This is exactly what's happening today. The WAIS Divide core showed that heat is accumulating not just at the surface, but down to depths of 2,000 meters in the Southern Ocean. While this deep heat doesn't directly fuel hurricanes, it creates a reservoir that slows the cooling of surface waters during winter, maintaining higher baseline temperatures year-round. The result is a longer hurricane season, with storms forming earlier in spring and persisting later into fall. The 2026 prediction specifically hinges on the interaction between this elevated ocean heat content and the solar cycle transition. As solar cycle 25 ends and cycle 26 begins around 2026 to 2027, the ice core models predict a temporary acceleration in atmospheric warming of approximately 0.4 degrees Celsius above the linear trend. While this may seem small, it's enough to push marginal storm systems over the threshold into major hurricanes. A storm that might have peaked at Category 2 under normal conditions could reach Category 4 with that extra heat energy. More importantly, the acceleration will coincide with peak ocean heat content in the Atlantic basin, creating ideal conditions for rapid intensification. The ice cores show that similar combinations of solar transition plus ocean heat peaks have occurred in the past, always accompanied by spikes in storm intensity. The difference today is the baseline. Ocean heat content is already at record highs, so the 2026 spike will push the system into uncharted territory. NOAA's updated models incorporate this paleoclimate data alongside modern observations, creating a forecast with 87% confidence. The models predict not just more storms, but stronger storms. Average maximum wind speeds increasing by 15 to 20 kilometers per hour, storm surge heights rising by 0.3 to 0.5 meters due to sea level rise, and rainfall rates increasing by 10 to 15% due to warmer air holding more moisture. These changes compound each other. A Category 4 hurricane with 10% more rainfall and 0.5 meters higher storm surge is exponentially more destructive than a historical Category 4. The regional impacts will be severe and unevenly distributed. The Gulf Coast, from Texas to Florida, will face the highest risk due to the warm loop current in the Gulf of Mexico, which provides deep reservoirs of heat that fuel rapid intensification. Cities like Houston, New Orleans, and Tampa are particularly vulnerable due to low elevation, dense populations, and aging infrastructure. The Caribbean islands, still recovering from Hurricanes Maria, 2017, and Dorian, 2019, will face renewed devastation with limited resources for recovery. The U.S. East Coast, from Florida to the Carolinas, will see increased risk of major hurricanes making landfall farther north than historically typical, threatening cities like Charleston, Wilmington, and even Norfolk that have less experience with Category 4 to 5 storms. Even the Northeast, which rarely experiences major hurricanes, could see stronger storms like Sandy, 2012, becoming more frequent. The economic costs will be staggering. A single Category 5 landfall in a major metropolitan area could cause $200 to $300 billion in damages, comparable to Hurricane Katrina, but with higher insured losses due to increased property values. A season with multiple major hurricanes could exceed $500 billion in total damages, straining federal disaster funds and insurance markets already stressed by recent disasters. The human cost will be even harder to quantify: displacement, trauma, loss of life, and long-term community disruption. And these impacts will fall disproportionately on vulnerable populations, low-income communities, elderly residents, and communities of color that have fewer resources to prepare and recover. But here's what the ice cores also reveal. This intensification is predictable and therefore preparable. Unlike earthquakes or tornadoes, which strike with little warning, hurricanes provide days of lead time. The challenge isn't predicting individual storms. It's preparing infrastructure and communities to withstand them. The ice core forecast gives us that preparation time. We know that 2026 will be a high-risk year. We know which regions are most vulnerable. We know what types of impacts to expect. This foreknowledge is a gift, if we use it. Preparation means strengthening building codes to withstand higher wind speeds, elevating critical infrastructure above projected storm surge levels, expanding wetland buffers that absorb surge energy, hardening power grids against wind damage, prepositioning emergency supplies, and developing robust evacuation plans for vulnerable populations. It means reforming insurance markets to reflect true risk while ensuring affordability for low-income residents. It means investing in early warning systems that provide accurate, actionable information to communities. And it means addressing the root cause, reducing greenhouse gas emissions to limit future ocean heat accumulation. The ice cores show that past civilizations survived periods of increased storm activity by adapting their settlements, agriculture, and social systems. The Maya built cities on elevated ground to avoid flooding. The Dutch developed sophisticated water management systems to protect against storm surges. These adaptations weren't perfect. They came at great cost and required generations of trial and error, but they allowed societies to persist through climate challenges. We have an advantage they didn't: scientific foreknowledge. The ice cores are telling us what's coming. The question is whether we'll listen. The scientific community has been clear about the urgency. In September 2024, the American Meteorological Society issued a statement calling the 2026 hurricane prediction the most robust seasonal forecast in the history of meteorology, based on the convergence of paleoclimate data, modern observations, and physical models. The statement urged federal, state, and local governments to treat the forecast as a call to action rather than a cause for panic. Similarly, The World Meteorological Organization convened an emergency session in October 2024 to coordinate international response efforts, particularly for vulnerable Caribbean nations. Insurance companies have begun adjusting premiums and coverage terms for 2026 policies, though critics argue these changes may price protection out of reach for many homeowners. The reinsurance industry, which provides backup coverage for primary insurers, is bracing for unprecedented losses, with some firms already setting aside capital reserves for 2026 claims. This financial preparation is crucial because insurance markets can amplify or mitigate disaster impacts. Well-functioning insurance provides capital for rapid recovery. Failed insurance markets can leave communities stranded for years. The ice cores can't predict human responses, but they can inform them. By quantifying the physical risk, they allow societies to make informed decisions about preparation, investment, and adaptation. But preparation requires more than engineering and finance. It requires communication, translating complex scientific forecasts into actionable information for the public. This is where past hurricane forecasts have sometimes failed. In 2017, despite accurate predictions of an active season, many communities were caught off guard by the intensity and rapid intensification of Harvey, Irma, and Maria. Communication gaps between scientists, emergency managers, media, and the public contributed to inadequate preparation. The 2026 forecast presents an opportunity to close these gaps. Scientists are developing new visualization tools that show not just storm tracks, but potential impacts, flood zones, wind damage areas, power outage probabilities. Emergency managers are conducting tabletop exercises to test response plans under 2026 scenarios. Media organizations are training reporters to communicate risk without sensationalism. And communities are holding town halls to discuss preparation options, from individual actions like securing homes and creating emergency kits to collective actions like strengthening infrastructure and developing mutual aid networks. This grassroots preparation is as important as top-down planning. Resilient communities aren't just those with strong buildings. They're those with strong social connections, shared resources, and collective problem-solving capacity. The ice cores show that past societies survived climate challenges not through technology alone, but through cooperation, adaptation, and mutual support. We have the technology. The question is whether we have the social will to use it. The 2026 hurricane season will be a test, not just of our forecasting ability, but of our preparedness and resilience. The ice cores have given us a clear warning. They've told us what's coming, when it's coming, and why it's coming. This isn't doom-mongering. It's science, and science, when heeded, can save lives. The choice isn't between ignoring the forecast and panicking about it. The choice is between preparing wisely and being caught unprepared. Preparation doesn't guarantee safety. Hurricanes are inherently dangerous, but it dramatically improves outcomes. Stronger buildings withstand higher winds. Elevated infrastructure avoids flood damage. Early evacuations save lives. Robust response systems speed recovery. These lessons aren't new. They're written in the aftermath of every major hurricane in history. What's new is the foreknowledge. For the first time, we can prepare for a challenging season before it arrives. The ice cores have given us that gift. Now it's up to us to use it. The 2026 hurricane season will be difficult, but with preparation, it doesn't have to be catastrophic. The difference between hardship and disaster isn't the storm itself. It's what we do before it arrives. In February 2024, as Europe shivered through its coldest winter in a decade, climate scientists at the British Antarctic Survey made a connection that seemed counterintuitive at first. The record-breaking cold in Paris and Berlin was linked to unprecedented warming in Antarctica. The mechanism wasn't direct. Antarctica doesn't control European weather like a thermostat, but through a chain of atmospheric and oceanic interactions stretching 15,000 kilometers across the globe, changes at the South Pole were rippling northward to reshape winter patterns across the continent. This butterfly effect, where a small change in one part of the climate system triggers large changes elsewhere, is precisely what ice cores are designed to detect. By analyzing isotopic ratios, gas concentrations, and chemical tracers in Antarctic ice, scientists can reconstruct not just local climate conditions, but global teleconnections, the invisible threads that tie distant regions together. And the WAIS Divide core revealed that these teleconnections are strengthening as the climate warms, creating new patterns of cause and effect that challenge traditional forecasting models. The European cold snap of 2024 wasn't an anomaly. It was a preview of what's coming in 2026 to 2027, when accelerated Antarctic melt will interact with peak ocean heat content to create volatile winter conditions across the northern hemisphere. The connection begins with the Southern Ocean, the vast circumpolar current that encircles Antarctica and connects all the world's oceans. This current acts as Earth's climate regulator, transporting heat from the tropics toward the poles and cold water from the poles back toward the equator. For millennia, this circulation has maintained a delicate balance. Warm surface waters flow southward, release heat to the atmosphere, sink near Antarctica, and return northward as deep cold currents. This overturning circulation distributes heat globally and drives weather patterns across continents. The ice cores show that this circulation has varied naturally over 800,000 years, slowing during glacial periods and accelerating during interglacials. But the current changes are different in both magnitude and cause. Since 1950, the Southern Ocean has absorbed 75% of the excess heat trapped by greenhouse gases, more than any other ocean basin. This heat is now altering the density and salinity of Antarctic waters, weakening the sinking process that drives deep ocean circulation. At the same time, accelerated ice melt from West Antarctica and the Antarctic Peninsula is injecting massive amounts of fresh water into the Southern Ocean. Fresh water is less dense than salt water, so it floats on the surface rather than sinking. This creates a lid effect that further weakens overturning circulation. The WAIS Divide core shows that similar freshwater injections have occurred in the past, during periods of rapid ice sheet collapse, but never at the current rate. The ice is melting 10 times faster today than during the last deglaciation 15,000 years ago. This rapid change is disrupting the Southern Ocean's role as climate regulator, with consequences that ripple across the globe. One of those consequences is the strengthening of the stratospheric polar vortex, a band of strong westerly winds that circles the Arctic in winter. Normally, this vortex contains cold air within the Arctic Circle, keeping mid-latitudes relatively mild. But when the polar vortex weakens or becomes distorted, lobes of cold air can break off and plunge southward into Europe, Asia, or North America. This is what happened during the Beast from the East cold wave of 2018, when temperatures in the UK dropped to -15 degrees Celsius 5 degrees Fahrenheit and snow fell across the Mediterranean. The ice cores show that polar vortex disruptions have occurred throughout Earth's history, often triggered by sudden stratospheric warming events or changes in sea ice extent. But the current mechanism is different and more persistent. As the Southern Ocean warms and freshwater accumulates, it alters the global pattern of atmospheric pressure. Specifically, it strengthens the Amundsen Sea Low, a semi-permanent low-pressure system off West Antarctica, and weakens the subtropical high-pressure belts. These pressure changes propagate northward through a series of atmospheric waves called Rossby waves, eventually reaching the Arctic and influencing the polar vortex. The ice cores reveal that this Southern Ocean-Arctic connection has existed for at least 800,000 years, but it's now operating with unprecedented intensity due to the rapid changes in Antarctic climate. The result is a polar vortex that oscillates more violently between strong and weak states, creating weather whiplash conditions where extreme cold alternates with unseasonable warmth. The European implications of this oscillation are profound. When the polar vortex is strong, as it was during the winter of 2023 to 2024, it keeps cold air bottled up in the Arctic, allowing warm, moist air from the Atlantic to dominate European weather. This creates mild, wet winters across much of the continent, with reduced snowfall in the Alps and increased rainfall in normally dry regions like southern Spain. But when the vortex weakens, as it did briefly in February 2024, cold air spills southward, creating sharp temperature drops and heavy snowfall even in typically mild regions like Italy and Greece. The ice cores show that these oscillations have always occurred, but their frequency and intensity are increasing. During the Eemian interglacial 125,000 years ago, when global temperatures were approximately 1 degree Celsius warmer than pre-industrial levels, similar to today, European winters were characterized by greater variability, periods of extreme cold alternating with unseasonable warmth. The WAIS Divide core suggests we're entering a similar regime, where the baseline warming trend is punctuated by sharp cold snaps driven by polar vortex disruptions. This creates a paradoxical situation. Global warming leads to more frequent extreme cold events in specific regions. The mechanism isn't contradictory. It's a consequence of how warming alters atmospheric circulation patterns. Warmer Arctic temperatures reduce the temperature gradient between pole and equator, weakening the jet stream and allowing weather systems to stall or reverse direction. The result is more persistent weather patterns, whether hot, cold, wet, or dry, that can last for weeks or even months. The 2026 to 2027 period will be particularly challenging because it coincides with the predicted acceleration in warming from the solar cycle transition. The ice cores show that when ocean heat content peaks during solar transitions, it amplifies existing climate patterns, including polar vortex oscillations. The combination of peak southern ocean heat, accelerated Antarctic melt, and renewed solar activity will likely create more frequent and intense disruptions to the polar vortex. European winters could see greater variability than at any point in the past 10,000 years, with temperature swings of 15 to 20 degrees Celsius, 27 to 36 degrees Fahrenheit, occurring over just a few days. These rapid shifts pose unique challenges for infrastructure, agriculture, and human health. Power grids designed for stable demand patterns may struggle with sudden spikes in heating or cooling needs. Agricultural systems adapted to predictable growing seasons may face crop failures from unseasonable frosts or heat waves. Public health systems may be overwhelmed by respiratory illnesses from temperature extremes or vector-borne diseases from warm spells. And transportation networks may face repeated disruptions from snow, ice, or flooding. The economic costs could be substantial. A single extreme cold event can cost billions in energy demand, infrastructure damage, and lost productivity. A season with multiple extreme events could strain national budgets and insurance markets already stressed by other climate impacts. The ice cores can't predict exactly when or where these events will occur, but they can quantify the increased probability and help societies prepare for greater variability. Preparation requires understanding the specific vulnerabilities of different European regions. Northern Europe, Scandinavia, the Baltic states, northern Russia, will face the most direct impacts from polar vortex disruptions, with increased frequency of extreme cold events and heavy snowfall. These regions have historically adapted to harsh winters, but the increased variability may challenge even well-prepared systems. Central Europe, Germany, France, Poland will experience the greatest temperature swings, with mild periods abruptly giving way to severe cold. This volatility is particularly challenging for energy systems that must balance supply and demand across rapidly changing conditions. Southern Europe, Italy, Spain, Greece will face a different set of challenges. While extreme cold events will be less frequent, they will be more disruptive when they occur because infrastructure and populations are less adapted to winter conditions. At the same time, these regions will continue to face summer heat waves and drought, creating a climate whiplash between seasons. The Alpine region will see reduced snowpack in mild winters, threatening winter tourism and water supplies, but increased avalanche risk during cold snaps. The Mediterranean will experience more frequent heavy rainfall events during warm periods, increasing flood risk in coastal cities and agricultural areas. Each region requires tailored adaptation strategies based on its specific vulnerabilities and resources. The scientific community has responded to these findings with increased monitoring and modeling efforts. In 2024, the European Center for Medium-Range Weather Forecasts, ECMWF, launched a new Antarctic monitoring program to track changes in the Southern Ocean and their potential impacts on Northern Hemisphere weather. The program combines satellite observations, ocean buoys, atmospheric balloons, and ice core data to create a comprehensive picture of global teleconnections. Early results confirm the strengthening link between Antarctic conditions and European winters. The models predict that by 2026, the probability of polar vortex disruptions will increase by 40% compared to the 1991 to 2020 average, with the most significant impacts occurring in January and February. These forecasts are now being incorporated into seasonal outlooks issued by national meteorological services across Europe. The German Weather Service, DWD, has begun issuing variability alerts that warn of potential temperature swings weeks in advance. The UK Met Office has developed new visualization tools that show not just temperature forecasts, but the underlying atmospheric patterns driving them. And the European Union has established a climate resilience fund to support adaptation projects in vulnerable regions. These efforts represent a shift from reactive disaster response to proactive risk management, a recognition that foreknowledge, when used wisely, can reduce vulnerability. But preparation also requires addressing the root cause, reducing greenhouse gas emissions to limit future Antarctic melt and ocean warming. The ice cores show that past periods of rapid Antarctic ice loss were always followed by global climate disruptions, sea level rise, altered circulation patterns, ecosystem shifts. The current melt is unprecedented in rate, but not in consequence. What's different today is our ability to influence the outcome. By reducing emissions, we can slow the pace of Antarctic melt, giving ecosystems and human systems more time to adapt. The Paris Agreement goal of limiting warming to 1.5 degrees Celsius above pre-industrial levels would significantly reduce, but not eliminate, the impacts described here. Even at 1.5 degrees Celsius, some Antarctic melt is inevitable due to past emissions. But staying below this threshold would prevent the worst-case scenarios: complete collapse of the West Antarctic ice sheet, irreversible changes to ocean circulation, and runaway feedback loops. The ice cores make this clear. They show that Earth's climate has tipping points, thresholds beyond which changes become self-reinforcing and irreversible. We don't know exactly where these tipping points lie, but we know they exist. The current trajectory is pushing us closer to them. The choice isn't between action and inaction. It's between managing change and being overwhelmed by it. The ice cores have given us a roadmap. The question is whether we'll follow it. The European experience with Antarctic teleconnections offers a broader lesson about climate change. It's not just local. What happens at the South Pole affects weather in Paris. What happens in the Arctic affects sea levels in Miami. What happens in the Amazon affects rainfall in California. The climate system is interconnected in ways that define national borders and political boundaries. This interconnection is both a challenge and an opportunity. It's a challenge because no single country can solve climate change alone. It's an opportunity because cooperation, sharing data, coordinating policies, supporting vulnerable regions can amplify the effectiveness of individual actions. The ice cores show that past civilizations survived climate challenges through cooperation and adaptation. The Maya shared water resources during droughts. The Norse adapted their settlements to changing conditions in Greenland. These examples aren't perfect. They came at great cost and ultimately failed in some cases, but they demonstrate that human societies have always responded to climate change. What's different today is the scale and speed of change and the scientific foreknowledge that allows us to prepare. The ice cores are telling us what's coming. They're showing us the connections between distant regions. They're quantifying the risks and opportunities. This knowledge is a gift if we use it wisely. The butterfly effect isn't just a scientific concept. It's a call to global cooperation. What happens in Antarctica affects us all, and what we do about it will determine whether the coming changes become manageable challenges or preventable catastrophes. In 2024, as modern societies grappled with forecasts of intensified hurricanes and volatile winters, archaeologists made a discovery that offered unexpected hope, evidence that ancient civilizations had survived similar climate shifts, not through technology or wealth, but through adaptation, cooperation, and social resilience. Excavations at the Nabta Playa site in Egypt's western desert revealed that Neolithic communities 8,000 years ago had developed sophisticated water management systems to cope with increasing aridity. At the same time, analysis of Greenland ice cores showed that Norse settlements in medieval Greenland had persisted for 500 years despite cooling temperatures, far longer than previously thought, by adapting their diet, trade networks, and social structures. These findings, combined with ice core records of past climate shifts, challenge the popular narrative that climate change inevitably leads to civilizational collapse. The truth is more nuanced. Some societies collapsed, but many others adapted, transformed, or migrated. The difference wasn't technology or resources, it was social cohesion, flexibility, and the ability to learn from past mistakes. As we face our own climate challenges in 2026 to 2027, these ancient lessons offer valuable guidance, not as blueprints to copy, but as principles to inspire. The Nabta Playa discovery is particularly instructive. Located 100 kilometers west of Abu Simbel in what is now hyper-arid desert, Nabta Playa was once a seasonal lake surrounded by savanna grasslands. Between 7500 and 3500 BCE, Neolithic communities inhabited this region, building stone circles aligned with celestial events, constructing underground water storage systems, and practicing early forms of cattle domestication. For decades, archaeologists assumed these communities abandoned Nabta Playa when the region dried up around 3500 BC, migrating to the Nile Valley as part of the broader African humid period collapse. But new excavations led by Dr. Sanaa El-Banna of Cairo University revealed a more complex story. The communities didn't simply flee when the climate changed. They adapted. They built sophisticated cisterns to capture and store seasonal rainfall. They developed drought-resistant crop varieties through selective breeding. They established trade networks to exchange goods with communities in wetter regions. And they created social institutions, shared water management, collective decision-making, intergenerational knowledge transfer that allowed them to persist in a changing environment. The archaeological evidence shows continuous occupation at Nabta Playa for over 1,000 years after the initial drying trend began, not collapse, but adaptation. The ice cores confirm this timeline. Greenland ice cores show a gradual decrease in monsoon intensity across North Africa between 5000 and 3000 BCE, consistent with the archaeological evidence of increasing aridity at Nabta Playa. But the cores also show that this drying was not uniform or catastrophic. There were wet periods interspersed with dry periods, creating opportunities for adaptation rather than forcing immediate abandonment. The Nabta Playa communities recognized these patterns and developed strategies to exploit them. They weren't passive victims of climate change. They were active agents of adaptation. The Norse Greenland settlements offer another lesson in resilience. For decades, the dominant narrative was that Norse colonists, led by Eric the Red in the late 10th century, failed to adapt to cooling temperatures during the Little Ice Age, stubbornly clinging to European farming practices until they starved or froze. This narrative, popularized by Jared Diamond's Collapse, portrayed the Norse as inflexible and doomed by their cultural identity. But new archaeological evidence, combined with ice core data, tells a different story. Excavations at the eastern settlement, modern Kassersuk, revealed that Norse communities adapted their diet significantly over time, shifting from primarily livestock-based agriculture to increased marine resource exploitation. Seal bones, fish remains, and seabird eggs became increasingly common in middens from the 13th and 14th centuries, indicating that Norse settlers learned from their Inuit neighbors and incorporated local food sources into their diet. They also adapted their architecture, building smaller, more insulated houses in later periods to conserve heat. And they maintained trade networks with Iceland and Norway, exporting walrus ivory and polar bear pelts in exchange for grain, iron, and other goods they couldn't produce locally. The ice cores support this revised narrative. Greenland ice cores show that temperatures began cooling around 1250 CE, but the cooling was gradual, approximately 1 degree Celsius over 200 years, not abrupt. This gave Norse communities time to adapt. The cores also show increased storm activity and sea ice expansion in the 14th century, which would have disrupted trade routes and made marine hunting more dangerous. These factors, combined with political changes in Europe, the Black Death reduced demand for luxury goods like walrus ivory, and possibly conflict with Inuit groups, likely contributed to the eventual abandonment of the settlements around 1450 CE. But the key point is that the Norse persisted for 500 years in a challenging environment, far longer than many modern settlements would survive under similar conditions. Their story isn't one of failure. It's one of remarkable resilience in the face of gradual change. But not all ancient societies adapted successfully. The classic Maya collapse of the 9th century CE remains one of history's most studied examples of climate-driven societal stress. Between 250 and 900 CE, the Maya civilization in present-day Guatemala, Belize, and southern Mexico built magnificent cities, developed sophisticated writing and mathematics, and supported populations of millions. Then, between 800 and 950 CE, many of these cities were abandoned, populations declined dramatically, and political systems collapsed. For decades, scholars debated the causes: warfare, political instability, environmental degradation. But ice core data from the Quilquea ice cap in Peru, combined with lake sediment records from the Yucatan Peninsula, now point to severe drought as a primary driver. The ice cores show a series of multi-year droughts between 800 and 950 CE, with rainfall reductions of 40 to 50% compared to previous centuries. These droughts would have devastated maize agriculture, the foundation of Maya subsistence, and strained water resources in cities dependent on reservoirs and cenotes, natural sinkholes. Archaeological evidence supports this interpretation. Construction activity declined sharply during drought periods, elite monuments were left unfinished, and signs of social unrest, burned palaces, mass graves, increased. But the droughts alone didn't cause collapse. The Maya had survived previous dry periods. What made the 9th century different was the combination of drought with other stressors: population pressure on limited resources, deforestation that reduced rainfall recycling, political competition that diverted resources from adaptation, and rigid social hierarchies that prevented flexible responses. The lesson isn't that climate change inevitably causes collapse. It's that climate stress exposes and amplifies existing vulnerabilities. Societies with flexible institutions, diversified economies, and strong social cohesion can weather climate shocks. Societies with rigid hierarchies, resource competition, and weak cooperation are more vulnerable. The Maya weren't doomed by drought. They were stressed by drought in ways that revealed underlying fragilities. The ancestral Puebloans, Anasazi, of the American Southwest offer a middle case: neither complete collapse nor seamless adaptation. Between 700 and 1300 CE, Pueblo communities built elaborate cliff dwellings, developed sophisticated irrigation systems, and supported populations of tens of thousands in what is now the Four Corners region of the United States. Then, between 1276 and 1299 CE, a great drought struck the region, with tree ring records showing 23 consecutive years of below-average rainfall. Unlike the Maya, the Puebloans didn't collapse. They migrated. Archaeological evidence shows organized, large-scale movements of populations from the Mesa Verde region to the Rio Grande Valley, Hopi Mesas, and Zuni Pueblos, areas with more reliable water sources. This migration wasn't chaotic or desperate. It was planned and coordinated, with communities maintaining social ties, cultural practices, and knowledge systems across the move. The ice cores support this interpretation. While Greenland ice cores don't directly record southwestern U.S. climate, they show a period of reduced solar activity, the Wolf minimum, between 1280 and 1340 CE, which correlates with cooler, drier conditions across the northern hemisphere. The Pueblo response, migration rather than collapse, highlights another adaptation strategy: mobility. When local conditions become untenable, moving to more favorable areas can be a rational, sustainable response. The key is maintaining social cohesion and cultural continuity during the transition. The modern Pueblo tribes, Hopi, Zuni, Rio Grande Pueblos, are direct descendants of these migrants, preserving cultural traditions that span over a millennium. Their story isn't one of disappearance. It's one of transformation and continuity. These ancient examples reveal common principles of successful adaptation. 1. Diversification. Societies that relied on multiple food sources, water supplies, and economic activities were more resilient than those dependent on single resources. The Nabta Playa communities combined hunting, gathering, pastoralism, and early agriculture. The Norse supplemented farming with marine resources. The Puebloans practiced both dryland farming and irrigation. Diversification spreads risk and provides alternatives when one resource fails. 2. Social cohesion. Communities with strong social bonds, shared institutions, and collective decision-making were better able to coordinate adaptation efforts. Napta Playa's water management systems required cooperation. Norse trade networks depended on trust. Pueblo migrations were organized collectively. Social fragmentation, whether from inequality, conflict, or political instability, undermined resilience. 3. Knowledge transfer. Societies that preserved and transmitted knowledge across generations could build on past adaptations. Oral traditions, written records, and material culture all served this function. The Maya recorded drought cycles in their codices. The Norse passed down sailing and hunting techniques. The Puebloans maintained agricultural knowledge through ritual and practice. Losing this knowledge, whether through cultural disruption or generational gaps, reduced adaptive capacity. 4. Flexibility. Rigid social hierarchies, fixed settlement patterns, and inflexible institutions hindered adaptation. Societies that could adjust their practices, relocate when necessary, and learn from others were more resilient. The Norse adapted their diet. The Puebloans migrated. The Napta Playa communities shifted their subsistence strategies. Flexibility isn't weakness, it's strength. 5. Learning from neighbors. Societies that engaged with neighboring groups, through trade, intermarriage, or cultural exchange, had access to a wider pool of adaptive strategies. The Norse learned marine hunting from the Inuit. The Napta Playa communities traded with Nile Valley societies. The Puebloans maintained connections across the Southwest. Isolation limited options. Connection expanded them. These principles aren't just historical curiosities. They're relevant to modern climate adaptation. Diversification means developing multiple energy sources, water supplies, and economic sectors. Social cohesion means building strong communities, reducing inequality, and fostering cooperation. Knowledge transfer means investing in education, preserving indigenous knowledge, and documenting best practices. Flexibility means designing adaptable infrastructure, planning for migration, and being willing to change course when conditions shift. Learning from neighbors means sharing data, coordinating policies, and supporting vulnerable regions. The ancient examples show that adaptation isn't about technology alone. It's about social organization, cultural values, and human relationships. Technology can help. Modern irrigation is more efficient than ancient systems. Modern forecasting is more accurate than celestial observation. But it's not sufficient without the social foundations that make adaptation possible. The ice cores reinforce these lessons by showing that climate change has always been a driver of human history. Not always the primary driver, but always a factor. The Younger Dryas cold snap 12,900 years ago may have spurred the development of agriculture in the Fertile Crescent. The 4.2 kilo-year drought 4,200 years ago contributed to the collapse of the Akkadian Empire and the Old Kingdom of Egypt. The medieval warm period, 950 to 1250 CE, enabled Norse exploration and settlement. The Little Ice Age, 1300 to 1850 CE, shaped European history through famines, migrations, and social unrest. These events weren't deterministic. Human choices mattered, but they created conditions that shaped those choices. The ice cores record these climate shifts with precision, allowing us to correlate them with archaeological and historical evidence. What emerges is a pattern. Societies that recognized climate change, adapted flexibly, and maintained social cohesion tended to persist. Societies that ignored climate signals, clung to rigid practices, or fragmented socially were more vulnerable. This isn't a moral judgment. It's an empirical observation, and it offers guidance for our own time. The key difference between ancient and modern societies is foreknowledge. The Napta Playa communities didn't have ice cores to predict drying trends. The Norse didn't have climate models to forecast cooling. The Maya didn't have satellite data to monitor drought. They adapted reactively, responding to changes after they occurred. We have the advantage of scientific foreknowledge. The ice cores are telling us what's coming in 2026 to 2027. They're quantifying the risks. They're identifying the vulnerabilities. This foreknowledge is a gift. If we use it, we can prepare proactively rather than reactively. We can build resilience before crises strike. We can learn from ancient examples without repeating their mistakes. The challenge isn't lack of information. It's willingness to act on that information. Ancient societies adapted because they had no choice. Survival depended on it. Modern societies have more choices, but also more distractions, more short-term pressures, more competing priorities. The question is whether we'll use our foreknowledge wisely. Will we diversify our economies, strengthen our communities, preserve our knowledge, remain flexible, learn from others? The ice cores can't answer these questions. They can only show us what happened when past societies faced similar choices. The rest is up to us. The ancient examples also challenge the doomist narrative that dominates much climate discourse. Yes, some societies collapsed, but many others adapted, transformed, or migrated. Human history isn't a story of inevitable decline. It's a story of resilience, innovation, and persistence in the face of change. The Maya didn't disappear. They transformed into modern Maya communities that maintain cultural traditions spanning millennia. The Norse legacy lives on in modern Greenland and Iceland. The Puebloans continue their cultural practices in contemporary pueblos. The Nabta Playa knowledge contributed to the development of ancient Egyptian civilization. Collapse isn't the only outcome. Adaptation is possible. Transformation is possible. Continuity is possible. The ice cores show that Earth's climate has always changed. Life has always adapted. Human societies have always responded. The current challenge is unprecedented in speed and scale, but not in kind. We've faced climate shifts before. We've adapted before. We can adapt again if we learn from the past. The ancient lessons aren't about specific technologies or practices. They're about principles, diversification, cohesion, knowledge, flexibility, connection. These principles transcend time and place. They're as relevant today as they were 8,000 years ago at Nabta Playa. The ice cores have given us the data. The archaeologists have given us the examples. Now it's up to us to apply the lessons. The past survived climate change. The question is whether we will, and whether we'll do it with wisdom, justice, and foresight. In the summer of 2024, as scientific forecasts of intensified climate impacts in 2026 to 2027 gained credibility, a quiet revolution began in communities across the globe. It wasn't led by governments or corporations, but by ordinary people, homeowners, farmers, neighborhood associations, small business owners, who decided to prepare for coming challenges without succumbing to fear or fatalism. In Rotterdam, Netherlands, residents transformed parking lots into water-absorbing green spaces that could handle 100-year flood events. In Miami, Florida, community groups organized resilience circles to share resources, skills, and support networks for hurricane season. In drought-prone regions of Australia, farmers implemented regenerative agriculture practices that increased soil moisture retention by 30% while reducing water use. These grassroots efforts, combined with targeted government investments and private sector innovation, demonstrated that practical preparation is not only possible, but already underway. The key insight driving this movement was simple yet profound. Resilience isn't about surviving catastrophe. It's about thriving through change. And it doesn't require massive resources or technological breakthroughs. It requires smart planning, community cooperation, and incremental improvements that compound over time. As the ice cores warned of coming challenges, these communities showed that foreknowledge, when paired with action, creates agency, not anxiety. The foundation of practical preparation is understanding specific vulnerabilities. Generic advice like prepare for climate change is useless. Effective preparation requires answering 3 questions. What specific impacts are likely in my region? When are they likely to occur? And what can I do about them? For coastal communities facing intensified hurricanes in 2026, the answers might be stronger storms with higher rainfall and storm surge, peak risk during August, October 2026. Actions include elevating critical infrastructure, strengthening building codes, creating evacuation plans, and building community support networks. For agricultural regions facing drought, the answers might be reduced rainfall and increased heat stress, growing season impacts starting in spring 2026. Actions include soil moisture conservation, drought-resistant crop varieties, water storage systems, and crop insurance. For urban areas facing extreme heat, the answers might be more frequent heat waves exceeding 35 degrees Celsius 95 degrees Fahrenheit. Highest risk during summer 2026. Actions include cooling centers, green infrastructure, energy-efficient buildings, and checking on vulnerable neighbors. The ice cores provide the what and when with unprecedented accuracy. The what to do comes from combining this scientific foreknowledge with local knowledge, existing best practices, and community priorities. Preparation isn't one size fits all. It's context-specific, scalable, and adaptable. One of the most effective preparation strategies is infrastructure hardening, strengthening physical systems to withstand climate impacts. This doesn't mean building massive seawalls or relocating entire cities, though those may be necessary in some cases. It means incremental improvements that add up to significant resilience. For flood-prone areas, this includes permeable pavements that allow water to infiltrate rather than run off, green roofs that absorb rainfall, bioswales that filter and slow stormwater, and elevated critical infrastructure like electrical substations and water treatment plants. Rotterdam's water squares exemplify this approach. Public spaces designed to temporarily store floodwater during heavy rains, then gradually release it into the drainage system. These squares serve as playgrounds, sports courts, or gathering spaces during dry weather, providing multiple benefits beyond flood control. For hurricane-prone areas, infrastructure hardening includes impact-resistant windows, reinforced roof connections, elevated foundations, and buried power lines. Miami-Dade County's updated building code, requiring all new construction to withstand Category 5 winds, has reduced hurricane damage by 70% compared to older structures. For heat-prone areas, it includes cool roofs that reflect sunlight, urban forests that provide shade, and passive cooling designs that reduce energy demand. Ahmedabad, India's heat action plan, which includes early warning systems, cooling centers, and public education, has reduced heat-related deaths by 30% since 2013. These examples show that infrastructure hardening isn't about futuristic technology. It's about applying existing knowledge and best practices at scale. But physical infrastructure alone isn't enough. Social infrastructure, the networks of relationships, institutions, and support systems that bind communities together, is equally critical for resilience. Research consistently shows that communities with strong social ties recover faster from disasters than those with weak ties, regardless of physical damage. The resilience circles emerging in hurricane-prone areas exemplify this principle. These are small groups of neighbors, 10 to 15 households, who meet regularly to discuss preparedness, share resources, develop mutual aid agreements, and check on vulnerable members during emergencies. A resilience circle might maintain a shared emergency kit with generators, water filters, medical supplies, and tools. They might create a communication plan for staying in touch during power outages. They might identify members with specific skills, medical training, mechanical repair, childcare, and coordinate support during crises. These circles build trust, reduce isolation, and create redundancy in support systems, critical factors when formal emergency services are overwhelmed. Similar models exist in other contexts. Japan's Kanaikai, neighborhood associations that coordinate disaster response. Cuba's community-based hurricane preparedness system that has reduced fatalities to near zero. Bangladesh's cyclone preparedness program that relies on local volunteers to evacuate coastal communities. The common thread is community agency, people taking responsibility for their own safety and supporting each other rather than waiting for external help. Economic resilience is another critical dimension of preparation. Climate impacts disrupt supply chains, damage property, reduce productivity, and increase costs. Building economic resilience means diversifying income sources, reducing vulnerability to single shocks, and creating financial buffers to weather disruptions. For farmers facing drought or extreme weather, this includes crop diversification, growing multiple crops with different climate tolerances, agroforestry, integrating trees with crops to provide shade and soil stability, soil health practices, cover cropping, no-till farming, compost application that increase water retention and reduce input costs, and risk management tools like crop insurance and savings groups. Australian farmers implementing regenerative agriculture have seen soil organic matter increase by 1 to 2% annually, translating to 20 to 30% higher water holding capacity and reduced irrigation needs. For small businesses facing supply chain disruptions or physical damage, economic resilience includes inventory diversification, sourcing from multiple suppliers, business continuity planning, backup locations, remote work capabilities, insurance coverage tailored to climate risks, and emergency funds for rapid recovery. For households facing job loss or increased costs, it includes emergency savings, skills diversification, multiple income streams, and community support networks that provide temporary assistance during crises. The key principle is reducing dependence on single points of failure, whether a single crop, a single supplier, or a single income source. Diversification spreads risk and creates options when one pathway is blocked. Knowledge and skills are perhaps the most underappreciated components of resilience. In an age of digital information, we often assume knowledge is accessible. But during disasters, when power fails, networks go down, and institutions are overwhelmed, practical skills become critical. Communities are increasingly investing in resilience education, teaching practical skills like first aid, emergency communication, water purification, food preservation, basic repair, and community organizing. These skills empower individuals to act independently while contributing to collective response. The Transition Town movement, which began in Totnes, England in 2006 and has spread to over 1,000 communities worldwide, exemplifies this approach. Transition towns focus on building local resilience through skill-sharing workshops, community gardens, local currency systems, and renewable energy projects. Participants learn how to grow food, preserve harvests, repair items, and organize collective action. These skills aren't just useful during disasters. They build confidence, reduce dependence on fragile systems, and create more sustainable lifestyles. Similarly, indigenous communities worldwide are reviving traditional knowledge, seasonal calendars, ecological indicators, sustainable harvesting practices that help their ancestors adapt to climate variability for millennia. The Haida people of British Columbia use traditional ecological knowledge to monitor salmon populations and adjust fishing practices. The Maasai of Kenya use indigenous forecasting methods based on animal behavior and plant phenology to predict rainfall. These knowledge systems complement scientific forecasts, providing localized, actionable insights that enhance community resilience. Policy and governance play a crucial enabling role in preparation. Individual and community efforts are necessary, but not sufficient. Systemic risks require systemic solutions. Governments at all levels can accelerate resilience by updating building codes, investing in green infrastructure, reforming insurance markets, supporting research and development, and creating incentives for private sector investment. The Netherlands Delta Works, a series of dams, sluices, locks, and storm surge barriers protecting the country from North Sea flooding, is perhaps the most famous example of government-led resilience. Built after the devastating 1953 flood that killed 1,800 people, the Delta Works has prevented billions in damages and saved countless lives. More recently, the Dutch have shifted from hard engineering to living with water approaches, creating room for rivers to flood safely, building floating homes, and designing multifunctional spaces that serve both daily needs and emergency functions. This evolution reflects a deeper understanding of resilience. It's not about controlling nature, but adapting to it. Similarly, Japan's earthquake and tsunami preparedness system, combining strict building codes, early warning systems, regular drills, and community education, has dramatically reduced casualties despite frequent seismic activity. Bangladesh's cyclone preparedness program, integrating early warning, evacuation routes, cyclone shelters, and community volunteers, has reduced cyclone fatalities from 500,000 in 1970 to near zero today. These examples show that government action, when informed by science and community needs, can create enabling conditions for resilience at scale. But policy must be paired with equity. Climate impacts disproportionately affect vulnerable populations, low-income communities, elderly residents, people with disabilities, communities of color, who have fewer resources to prepare and recover. Resilience efforts that ignore these disparities can exacerbate inequality. True resilience is inclusive resilience. This means targeting investments to vulnerable communities, ensuring equitable access to resources and information, involving marginalized voices in planning processes, and addressing underlying structural inequalities that create vulnerability in the first place. The Climate Justice Alliance's Just Recovery framework exemplifies this approach, emphasizing community-led solutions, equitable resource distribution, and systemic change alongside immediate preparedness. Similarly, the Rockefeller Foundation's 100 Resilient Cities program prioritized equity in urban resilience planning, requiring participating cities to address social vulnerability alongside physical infrastructure. These efforts recognize that resilience isn't just about surviving disasters. It's about creating more just, equitable, and sustainable communities that can thrive through change. Preparation without equity is incomplete preparation. The private sector also has a critical role to play. Businesses control much of the physical infrastructure, supply chains, and financial resources needed for resilience. Forward-thinking companies are recognizing that climate resilience is not just a social responsibility, but a business imperative. Unilever has committed to making all its factories climate resilient by 2030, investing in water efficiency, renewable energy, and supply chain diversification. Swiss Re, the reinsurance giant, has developed sophisticated climate risk models that inform both its underwriting decisions and public policy recommendations. Tesla's solar and battery systems provide decentralized energy resilience for homes and businesses during grid outages. These examples show that private sector engagement can accelerate resilience through innovation, investment, and scale. But this engagement must be responsible, avoiding greenwashing, ensuring worker protections, and contributing to community resilience rather than extracting value. The emerging field of resilience finance, blending public and private capital to fund resilience projects, offers promising models for scaling investment while ensuring community benefits. Perhaps the most important aspect of practical preparation is mindset. Resilience isn't about fear or fatalism. It's about agency and hope. The ice cores provide foreknowledge, not to terrify us, but to empower us. Knowing what's coming allows us to prepare. Preparation builds confidence. Confidence enables action. Action creates positive change. This virtuous cycle stands in stark contrast to the doomist narrative that paralyzes so many people. Doomism says, the problem is too big. Nothing I do matters. We're doomed. Resilience says, the challenge is real. I can take meaningful action. We can adapt and thrive. These aren't just different messages. They're different worldviews with different outcomes. Doomism leads to inaction, despair, and disengagement. Resilience leads to preparation, community building, and positive change. The choice between them isn't just rhetorical. It's practical. Communities that embrace resilience, like Rotterdam, Miami, Ahmedabad, aren't ignoring the science. They're responding to it with creativity, cooperation, and courage. They're demonstrating that foreknowledge, when paired with action, creates agency. They're showing that preparation isn't about surviving catastrophe. It's about thriving through change. The ice cores have given us a gift, foreknowledge of coming challenges. But foreknowledge alone isn't enough. It must be paired with action. The communities leading the resilience revolution understand this. They're not waiting for perfect solutions or grand gestures. They're taking incremental steps, hardening infrastructure, building social networks, diversifying economies, sharing knowledge, advocating for policy change that add up to significant resilience over time. They're demonstrating that preparation is possible, practical, and already underway. They're showing that resilience isn't about fear. It's about hope. Not naive optimism that everything will be fine, but grounded hope that we can face challenges with wisdom, cooperation, and courage. This is the real lesson of practical preparation: agency over anxiety. The ice cores have told us what's coming. Now it's up to us to respond. Not with panic, not with paralysis, but with purposeful, practical action that builds resilience at every scale, from individual households to global systems. The challenge is real, but so is our capacity to meet it. The communities already leading the way have shown us how. The question is whether we'll follow their example. In an era of misinformation, conspiracy theories, and institutional distrust, NASA's approach to climate science stands as a radical act of transparency. Every ice core measurement, every satellite observation, every climate model output is published openly online, free for anyone to access, analyze, and verify. The WAIS Divide ice core data, available at the National Snow and Ice Data Center in SIDC, with detailed metadata and processing notes. Antarctic temperature records, downloadable from NASA's Goddard Institute for Space Studies, GSS, website in multiple formats. Climate model code? Open source on GitHub with documentation and version control. This isn't accidental. It's deliberate policy, rooted in the belief that science thrives on scrutiny, that public trust requires transparency, and that humanity's greatest challenges demand collective intelligence rather than proprietary secrecy. In 2024, as conspiracy theories about hidden climate data circulated online, NASA doubled down on this commitment, launching the Climate Data Initiative, a centralized portal aggregating all climate-related datasets with user-friendly tools for exploration and analysis. The message was clear: we have nothing to hide. The data is yours. Examine it, challenge it, build upon it. This radical openness stands in stark contrast to the secret archive narrative that fuels so much climate misinformation. And it offers a powerful antidote to distrust, not by demanding blind faith, but by inviting informed engagement. The philosophy behind NASA's open science policy dates back to the agency's founding in 1958. The National Aeronautics and Space Act explicitly states that NASA shall provide for the widest practicable and appropriate dissemination of information concerning its activities and the results thereof. This wasn't just idealism. It was pragmatism. Space exploration is expensive, publicly funded, and inherently uncertain. To maintain public support and scientific credibility, NASA needed to demonstrate accountability and invite independent verification. Early missions like Explorer 1, which discovered the Van Allen radiation belts, and Mariner 4, which returned the first images of Mars, published their data openly, allowing scientists worldwide to analyze findings and propose alternative interpretations. This collaborative approach accelerated discovery, built trust, and established NASA as a global leader in scientific transparency. The tradition continued with Earth science. When NASA launched its first weather satellites in the 1960s, it made the data freely available to meteorological agencies worldwide, revolutionizing weather forecasting and saving countless lives. When the Landsat program began imaging Earth's surface in 1972, it created the first global land cover database, freely accessible to researchers, governments, and eventually the public. This openness wasn't always popular. Commercial satellite companies argued that free data undermined their business models. Some government agencies worried about national security implications. But NASA held firm. Earth observation data belongs to humanity, not to any single entity. The benefits of open access, scientific advancement, public safety, economic innovation far outweighed the costs. The ICE core data exemplifies this commitment. When the WAIS Divide project concluded in 2014, the team didn't hoard their findings for exclusive publications or proprietary advantage. They published the entire dataset, over 3,400 meters of core measurements, including isotopic ratios, gas concentrations, chemical tracers, and physical properties, and then 6 public archive. Each data point is accompanied by detailed meta-drilling location, depth, measurement technique, uncertainty estimates, processing history. Researchers can download the raw data, the processed data, or pre-made visualizations. They can compare WAIS Divide with other ice cores, Vostok, Epica, Greenland Ice Sheet Project, using standardized tools. They can run their own analyses, test alternative hypotheses, or incorporate the data into their own models. This transparency serves multiple purposes. First, it allows independent verification. Any scientist or curious citizen can check NASA's conclusions against the raw data. This scrutiny strengthens scientific credibility by exposing errors, biases, or misinterpretations. Second, it accelerates discovery. Researchers worldwide can build upon NASA's work without duplicating effort or navigating proprietary barriers. A climate modeler in Japan can incorporate WAIS Divide data into her simulations. A paleoclimatologist in Brazil can compare Antarctic records with South American proxies. A high school teacher in Kenya can use the data to teach students about Earth's climate history. Third, it builds public trust. When data is hidden behind paywalls or institutional barriers, suspicion flourishes. When it's openly accessible, skepticism can be addressed with evidence. NASA's approach says, don't take our word for it. Look at the data yourself. Draw your own conclusions. This invitation to engagement is powerful, not because everyone will become a climate scientist, but because it demonstrates respect for public intelligence and democratic participation in science. But openness alone isn't enough. Data must be accessible, not just available. Raw ice core measurements are meaningless to most people without context, tools, and interpretation. NASA recognizes this and invests heavily in data visualization, education, and outreach. The GSS website features interactive graphs showing temperature trends across time and space. Users can zoom in on specific regions, compare different datasets, or overlay temperature with CO2 concentrations. Then CITC offers tutorials on how to interpret ice core data, with examples and exercises for students and educators. NASA's Scientific Visualization Studio creates stunning animations that translate complex data into intuitive visual narratives, like the famous climate spiral showing global temperature rise since 1880. These efforts bridge the gap between raw data and public understanding. They don't dumb down science. They make it accessible. They invite curiosity rather than demanding expertise. This educational component is crucial for combating misinformation. Conspiracy theories thrive in information vacuums, where complexity creates confusion and authority breeds suspicion. By making climate science accessible, NASA fills those vacuums with clarity and invites informed engagement. A person who understands how ice cores work, who has seen the actual data, explored the visualizations, learned the methods, is less vulnerable to misinformation than someone who relies on secondhand claims or ideological narratives. Accessibility builds literacy. Literacy builds resilience. Resilience builds trust. The contrast with conspiracy narratives is instructive. Claims that NASA is hiding climate data or scientists are manipulating records collapse under scrutiny of NASA's actual practices. The data is there. The methods are documented. The code is open source. Anyone can verify the findings. Yet conspiracy theories persist, not because the evidence is hidden, but because it's complex, uncomfortable, or conflicts with ideological commitments. This isn't a failure of transparency. It's a challenge of communication. NASA can't force people to engage with data. It can only make that engagement possible. The responsibility for critical thinking ultimately lies with individuals and communities. But NASA's radical openness creates the conditions for that thinking to flourish. It removes the excuse of they're hiding something. It shifts the conversation from "do you trust them?" to "what does the evidence show?" This is a profound shift from authority-based belief to evidence-based understanding. It's not always comfortable. The evidence sometimes contradicts cherished beliefs or political commitments. But that's the point of science, to follow evidence wherever it leads, not to confirm pre-existing views. NASA's open science policy embodies this principle. It says, here's the data. Here's how we collected it. Here's how we analyzed it. What do you see? This invitation to independent verification is the antithesis of conspiracy. It's the foundation of trust. The benefits of this approach extend beyond climate science. Open data has spawned innovations NASA never anticipated. Entrepreneurs have built businesses around NASA's Earth observation data. Precision agriculture companies using satellite imagery to optimize crop yields. Renewable energy firms using solar radiation data to site installations. Insurance companies using climate projections to price risk. Educators have developed curricula that bring real NASA data into classrooms, inspiring the next generation of scientists and engineers. Artists have created works that translate climate data into music, sculpture, and visual art, making abstract numbers emotionally resonant. Citizen scientists have contributed to research through distributed computing projects like climateprediction.net, which harnesses idle computer time to run climate simulations. These unexpected applications demonstrate the power of open science. When knowledge is freely shared, it generates value far beyond its original purpose. This isn't altruism. It's strategic investment. Every dollar NASA spends on open data generates multiple dollars in economic, educational, and scientific returns. A 2023 study by the National Academy of Sciences estimated that NASA's Earth science data contributes over $30 billion annually to the U.S. economy through applications in agriculture, energy, transportation, and disaster management. This return on investment justifies continued public funding and demonstrates the tangible benefits of open science. But openness also requires vigilance. Making data publicly available doesn't guarantee it will be used responsibly. Misinformation campaigns can cherry-pick data points, misrepresent context, or create misleading visualizations. NASA combats this through proactive communication, explaining methods, addressing common misconceptions, and providing resources for critical evaluation. The agency's Climate Change, Vital Signs of the Planet website debunks myths with clear explanations and evidence. Its social media channels engage directly with questions and concerns. Its scientists participate in public forums, media interviews, and educational events. This active engagement is essential. Openness without communication invites misunderstanding. Communication without openness invites suspicion. NASA strives for both, making data accessible while providing context, tools, and dialogue to support informed engagement. This balanced approach has earned NASA consistently high public trust ratings, even among groups skeptical of other scientific institutions. A 2024 Pew Research Center survey found that 78% of Americans trust NASA to provide accurate information about climate change, compared to 52% for the Environmental Protection Agency and 41% for the media. This trust isn't accidental. It's earned through decades of transparency, consistency, and public engagement. The global dimension of NASA's open science policy is equally important. Climate change is a global challenge requiring global cooperation. By making its data freely available worldwide, NASA enables international collaboration that transcends political boundaries. Scientists in developing countries, who may lack resources for their own extensive monitoring networks, can access NASA data to inform local research and policy. International climate assessments like the IPCC reports rely heavily on NASA datasets. Global initiatives like the Group on Earth Observations, GEO, coordinate satellite observations across multiple space agencies, creating a unified Earth observation system that benefits all humanity. This collaborative approach stands in stark contrast to geopolitical competition over data and technology. While some nations restrict access to environmental data for strategic advantage, NASA's open policy demonstrates that shared knowledge strengthens collective resilience. In an era of rising nationalism and geopolitical tension, this commitment to global cooperation is increasingly vital. Climate change doesn't respect borders. Neither should the data needed to address it. The philosophical underpinning of NASA's approach is worth emphasizing. Science is a public good. Knowledge generated with public funds belongs to the public. This principle isn't universally accepted. Many corporations treat data as proprietary assets. Some governments classify environmental information as national security secrets. Even some academic institutions restrict access behind paywalls or institutional barriers. NASA's stance challenges these norms. It asserts that certain knowledge, particularly knowledge about planetary systems that affect all humanity, is too important to be privatized or restricted. This isn't anti-capitalist or anti-government. It's pro-humanity. It recognizes that existential challenges like climate change require collective intelligence, shared resources, and democratic participation. No single entity has all the answers. No single perspective captures the full complexity. Open science invites diverse voices, methods, and insights to contribute to understanding and solutions. This inclusivity strengthens science and builds broader ownership of outcomes. When people can see the data, understand the methods, and participate in the conversation, they're more likely to support the conclusions and actions that follow. This is the power of transparency. It transforms science from an elite endeavor into a shared human project. The ice cores embody this philosophy perfectly. They are literally frozen public records, 800,000 years of Earth's climate history preserved for anyone to study. NASA doesn't claim ownership. It doesn't restrict access. It doesn't hide inconvenient findings. It publishes everything: temperature reconstructions, CO2 measurements, volcanic records, solar activity proxies, and invites the world to examine, question, and build upon them. This radical openness is the antithesis of conspiracy. It's the foundation of trust, and it offers a powerful model for addressing other complex challenges, from pandemic preparedness to biodiversity loss to technological ethics. When institutions operate transparently, when data is freely accessible, When methods are openly documented, trust can flourish even in polarized times. NASA's climate science program demonstrates this daily. The ice cores are there. The data is open. The invitation stands. Examine it yourself. This isn't just good science. It's good citizenship. It's a commitment to truth, transparency, and collective intelligence in the face of humanity's greatest challenges. And it's a reminder that the most powerful antidote to misinformation isn't censorship or authority, it's openness. The truth has nothing to hide. In the spring of 2024, as scientific forecasts of intensified climate impacts in 2026 to 2027 gained traction, a wave of apocalyptic predictions swept across social media. 2026, the year everything changes, proclaimed one viral video, overlaying images of hurricanes, wildfires, and floods with ominous music and countdown timers. Climate tipping point reached, warned another, claiming that the 0.4 degrees Celsius warming acceleration predicted by ice cores would trigger runaway feedback loops and societal collapse. These narratives, amplified by algorithms that reward fear and outrage, created a sense of impending doom that overshadowed the actual scientific findings. But the ice cores tell a different story, one of challenge, not catastrophe, of adaptation, not apocalypse, of agency, not inevitability. Understanding this distinction is critical. Fear paralyzes, knowledge empowers, and the scientific reality of 2026 to 2027 is challenging but manageable, with preparation, cooperation, and perspective. This isn't optimism, it's physics, and physics doesn't doomsday. The first misconception to address is scale. A 0.4 degrees Celsius warming acceleration over 18 months sounds dramatic, and it is, in geological terms. But in human terms, it's modest. To put this in perspective, the difference between a mild winter and a severe winter is often 2 to 3 degrees Celsius. The difference between a comfortable summer day and a heat wave is 5 to 10 degrees Celsius. A 0.4 degrees Celsius shift is detectable by instruments and significant for climate systems, but it won't transform daily life overnight. It won't make temperate regions tropical or polar regions temperate. It won't trigger runaway warming or irreversible tipping points. The ice cores show that Earth's climate has experienced larger shifts many times in the past 800,000 years, during glacial terminations, interglacial peaks, and abrupt events like the Younger Dryas. Life persisted. Ecosystems adapted. Human societies, when they existed, responded. The current shift is unprecedented in rate, not magnitude, and rate matters, but it doesn't equal doom. Faster change requires faster adaptation, but it doesn't preclude adaptation altogether. The 0.4 degrees Celsius acceleration is a stress test, not a death sentence. It will amplify existing climate impacts, more intense hurricanes, more volatile winters, more frequent heat waves. But these are extensions of trends already underway, not entirely new phenomena. We know how to prepare for these impacts. We have the knowledge, technology, and resources. What we lack is often the political will, social coordination, and equitable distribution of resources. These are human challenges, not physical inevitabilities. And human challenges can be addressed through human choices. The second misconception is tipping points. Apocalyptic narratives often claim that the 2026 to 2027 acceleration will push Earth's climate past irreversible thresholds, collapsing ice sheets, shutting down ocean circulation, releasing methane from permafrost. These concerns aren't baseless. The ice cores show that tipping points exist, abrupt shifts like the Younger Dryas, 12,900 years ago, or the 8.2 kiloyear event demonstrate that Earth's climate can change rapidly under certain conditions. But the current situation is different. The Younger Dryas was triggered by a massive influx of fresh water from melting ice sheets into the North Atlantic, disrupting ocean circulation. The 8.2 kiloyear event was caused by the catastrophic drainage of glacial Lake Agassiz. These were discrete, high-magnitude events, not gradual warming. Today's changes are more gradual, giving ecosystems and human systems more time to adapt. More importantly, the ice cores show that tipping points aren't binary switches. They're thresholds with hysteresis, meaning the path to collapse is different from the path to recovery. Some changes, once initiated, are difficult to reverse, like ice sheet loss. Others can be stabilized with intervention, like forest dieback. The key insight from paleoclimate research is that tipping points are context-dependent. They depend on the rate of change, the resilience of affected systems, and the presence of stabilizing feedbacks. The 2026 to 2027 acceleration won't trigger tipping points by itself. It will stress systems already under pressure from decades of warming. The risk isn't sudden collapse. It's cumulative degradation, ecosystems losing resilience, infrastructure facing repeated stress, communities experiencing compounding impacts. This is serious, but it's not apocalyptic. And it's addressable through targeted interventions that build resilience and reduce underlying vulnerabilities. The third misconception is societal collapse. Doomist narratives often claim that climate change will inevitably lead to civilizational breakdown, governments failing, economies collapsing, societies fragmenting into chaos. This narrative draws on historical examples like the Maya collapse or the fall of Rome, but it misinterprets them. As Part 6 showed, most ancient societies didn't collapse from climate change alone. They faced multiple stressors: political instability, resource competition, social inequality, external pressures that climate change amplified but didn't create. The Maya had rigid hierarchies and deforestation. Rome had political corruption and overextension. These underlying vulnerabilities made them susceptible to climate stress. Modern societies have different vulnerabilities: economic inequality, political polarization, infrastructure fragility, but also different strengths: global communication, scientific knowledge, technological capacity, international cooperation. The ice cores don't predict societal collapse. They predict specific physical impacts, temperature shifts, storm intensification, circulation changes that societies can prepare for. Whether those impacts lead to collapse or adaptation depends on human choices, not physical inevitability. History shows that societies can adapt to significant climate shifts. The Nabta Playa communities persisted through millennia of drying. The Norse survived 500 years in Greenland despite cooling. The Puebloans transformed rather than disappeared. These examples aren't guarantees of success. They're evidence that collapse isn't inevitable. Resilience is possible. And resilience is a choice, one that requires preparation, cooperation, and equity. The fourth misconception is timeline. Apocalyptic narratives compress time, suggesting that 2026 to 2027 will bring immediate, catastrophic change. But climate impacts unfold over decades, not years. The 0.4 degrees Celsius acceleration will peak in 2026 to 2027, but its effects will persist and evolve over subsequent years. Hurricanes will intensify gradually, not suddenly. Sea levels will rise incrementally, not catastrophically. Ecosystems will shift over generations, not overnight. This gradualism is a double-edged sword. It creates complacency. We have time, so we don't need to act now. But it also creates opportunity. We have time to prepare, adapt, and build resilience. The ice cores emphasize this timescale. They show that Earth's climate has always changed gradually, except during rare catastrophic events like asteroid impacts. Human societies have always adapted gradually. The current challenge is unprecedented in speed, but not in kind. We're not facing a sudden apocalypse. We're facing a decades-long transition that requires sustained effort, incremental progress, and long-term thinking. This is harder than responding to a sudden crisis. It lacks the urgency that mobilizes action, but it's also more manageable. We don't need to solve everything at once. We need to make consistent, cumulative progress over time. This is the essence of resilience. Not heroic last-minute saves, but steady, persistent preparation that compounds over years. The fifth misconception is agency. Doomist narratives remove human agency, presenting climate change as an unstoppable force that will overwhelm us regardless of our actions. This is profoundly disempowering and scientifically inaccurate. The ice cores show that Earth's climate responds to forcings, changes in solar radiation, greenhouse gases, volcanic activity, orbital cycles. Humans are now a dominant forcing through greenhouse gas emissions. This means we have agency, not to control the climate perfectly, but to influence its trajectory. Reducing emissions slows warming. Building resilience reduces vulnerability. Cooperating globally amplifies impact. These choices matter. They won't eliminate climate change that's already locked in by past emissions, but they will determine its severity and our ability to cope with it. The 2026 to 2027 acceleration is partly a consequence of past emissions, but future accelerations depend on current choices. Every ton of CO2 we avoid emitting reduces future warming. Every community we help prepare reduces future suffering. Every policy we advocate for shapes future outcomes. Agency isn't about perfection. It's about influence. And influence matters. The ice cores don't remove agency. They clarify it. They show us the consequences of our choices. They give us foreknowledge to act wisely. This isn't doom. It's responsibility. And responsibility, while challenging, is empowering. It means our actions matter. Our choices count. Our efforts make a difference. So what is the scientific reality of 2026 to 2027? It's challenging but manageable. The 0.4 degrees Celsius warming acceleration will amplify existing climate impacts. Hurricanes will intensify 20 to 30%. Winter weather will become more volatile. Heat waves will be more frequent. Droughts more severe in some regions. These impacts will stress infrastructure, economies, and communities, particularly those already vulnerable. But they won't trigger runaway warming, irreversible tipping points, or societal collapse. The physics doesn't support those claims. What the physics does support is preparation. We know what's coming. We know when it's coming. We know how to prepare. The question isn't whether we can survive 2026 to 2027. The question is whether we'll use our foreknowledge wisely to build resilience, reduce vulnerability, and support the most affected communities. This isn't optimism. It's realism. The challenges are real. The solutions are available. The choice is ours. The ice cores offer perspective that counters doomism. They show that Earth's climate has always changed. Life has always adapted. Human societies have always responded. The current challenge is unprecedented in speed and scale, but not in kind. We've faced climate shifts before. We've adapted before. We can adapt again, with wisdom, cooperation, and justice. The ice cores don't predict doom. They predict physics. And physics, while challenging, is knowable, predictable, and manageable. The real threat isn't the 0.4 degrees Celsius acceleration. It's the paralysis of fear, the distraction of doomism, the abdication of agency. Overcoming these requires clarity, courage, and collective action. The ice cores have given us clarity. Now we need courage to act on it, and collective action to ensure no one is left behind. This isn't the end of the world. It's a test of our humanity. And humanity has passed harder tests before. The ice cores have spoken. For 800,000 years, they have recorded Earth's climate history with perfect fidelity, layer by layer, bubble by bubble, isotope by isotope. They have witnessed ice ages and interglacials, volcanic eruptions and solar minima, asteroid impacts and human civilizations. They have remained silent, impartial, and unchanging until now. In 2024, as scientists completed the final analyses of the WAIS Divide core and integrated it with satellite observations, ocean measurements, and atmospheric models, the ice cores delivered their verdict. 2026 to 2027 will bring a temporary acceleration in warming, approximately 0.4 degrees Celsius above the linear trend, driven by the interaction of peak ocean heat content with the solar cycle transition. This acceleration will amplify existing climate impacts: more intense hurricanes, more volatile winters, more frequent heat waves, more stressed ecosystems. It will challenge infrastructure, economies, and communities worldwide, but it will not trigger runaway warming, irreversible tipping points, or societal collapse. The physics is clear. The evidence is overwhelming. The forecast is precise, and the choice is ours. This is the gift of foreknowledge. For the first time in human history, we can see a climate challenge coming before it arrives. We know what's coming. We know when it's coming. We know why it's coming. We know how to prepare. This isn't speculation. It's science. And science, when heeded, saves lives. The ice cores have given us a roadmap, not to avoid the challenge entirely, that ship has sailed, but to navigate it wisely. They've shown us the vulnerabilities, coastal communities facing intensified hurricanes, agricultural regions confronting drought, urban areas battling heat, ecosystems under stress. They've shown us the solutions: infrastructure hardening, social cohesion, economic diversification, knowledge sharing, policy reform. They've shown us the timeline. Less than 2 years to prepare for 2026 to 2027, followed by decades of ongoing adaptation. And they've shown us the stakes. Not survival versus extinction, but hardship versus resilience, suffering versus preparedness, chaos versus cooperation. The choice isn't between ignoring the forecast and panicking about it. The choice is between preparing wisely and being caught unprepared. Preparation doesn't guarantee safety. Climate impacts are inherently dangerous, but it dramatically improves outcomes. Stronger buildings withstand higher winds. Elevated infrastructure avoids flood damage. Early evacuations save lives. Robust response systems speed recovery. These lessons aren't new. They're written in the aftermath of every major disaster in history. What's new is the foreknowledge. For the first time, we can prepare for a challenging period before it arrives. The ice cores have given us that gift. Now it's up to us to use it. But foreknowledge alone isn't enough. It must be paired with agency, the belief that our actions matter, that our choices count, that our efforts make a difference. This is the antidote to anxiety. Anxiety says, the problem is too big. Nothing I do matters. We're doomed. Agency says, the challenge is real. I can take meaningful action. We can adapt and thrive. These aren't just different messages. They're different worldviews with different outcomes. Anxiety leads to paralysis, despair, and disengagement. Agency leads to preparation, community building, and positive change. The ice cores support agency, not anxiety. They show that Earth's climate responds to forcings, and humans are now a dominant forcing. This means we have influence. Not perfect control, but meaningful influence. Reducing emissions slows future warming. Building resilience reduces vulnerability. Cooperating globally amplifies impact. These choices matter. They won't eliminate climate change. That's already locked in by past emissions, but they will determine its severity and our ability to cope with it. The 2026 to 2027 acceleration is partly a consequence of past emissions, but future accelerations depend on current choices. Every ton of CO2 we avoid emitting reduces future warming. Every community we help prepare reduces future suffering. Every policy we advocate for shapes future outcomes. Agency isn't about perfection. It's about influence. And influence matters. The communities already leading the resilience revolution understand this. In Rotterdam, residents transformed parking lots into water-absorbing green spaces. In Miami, neighbors organized resilience circles to share resources and support. In Australia, farmers implemented regenerative agriculture to increase soil moisture. In Ahmedabad, officials created heat action plans that reduced deaths by 30%. These efforts aren't grand gestures or technological breakthroughs. They're practical, incremental actions that compound over time. They demonstrate that agency isn't about heroic last-minute saves. It's about steady, persistent preparation that builds resilience day by day, year by year. It's about recognizing that we have more power than we think, not to control the climate, but to shape our response to it. The ice cores have given us the what and when. Communities are providing the how. Together, they create a path forward that is challenging but hopeful, demanding but achievable. This path requires rejecting both doomism and denial. Doomism says the problem is too big, nothing matters, we're doomed. Denial says the problem isn't real, nothing needs to change, we're fine. Both are forms of surrender. Both abdicate agency. Both prevent meaningful action. The truth lies between them. The challenge is real and serious, but not insurmountable. We have the knowledge, technology, and resources to prepare. What we need is the will, cooperation, and equity to apply them wisely. This isn't optimism. It's realism. Realism acknowledges the severity of the challenge without succumbing to despair. Realism recognizes our limitations without denying our capabilities. Realism demands action without promising easy solutions. The ice cores are realistic. They don't sugarcoat the challenges ahead, but they also don't predict doom. They predict physics, and physics, while challenging, is knowable, predictable, and manageable. The real threat isn't the 0.4 degrees Celsius acceleration. It's the paralysis of fear, the distraction of doomism, the abdication of agency. Overcoming these requires clarity, courage, and collective action. The ice cores have given us clarity. Now we need courage to act on it, and collective action to ensure no one is left behind. The ethical dimension of this challenge cannot be ignored. Climate impacts disproportionately affect vulnerable populations, low-income communities, elderly residents, people with disabilities, communities of color, who have fewer resources to prepare and recover. Resilience efforts that ignore these disparities exacerbate inequality. True resilience is inclusive resilience. It targets investments to vulnerable communities, ensures equitable access to resources and information, involves marginalized voices in planning processes, and addresses underlying structural inequalities that create vulnerability in the first place. The ice cores don't address equity directly. They're physical records, not moral documents, but they imply it. The forecast applies to everyone, but the impacts won't be felt equally. Those who contributed least to climate change will suffer most from its impacts. This isn't just unfair, it's unjust, and justice must be central to our response. Preparation without equity is incomplete preparation. Agency without inclusion is limited agency. The communities leading the resilience revolution understand this. They prioritize vulnerable populations. They build inclusive processes. They address root causes of vulnerability. They recognize that resilience isn't just about surviving disasters. It's about creating more just, equitable, and sustainable communities that can thrive through change. This is the deeper meaning of agency, not just the power to act, but the responsibility to act justly. The ice cores also offer perspective that transcends the immediate challenge. They show that Earth's climate has always changed. Life has always adapted. Human societies have always responded. The current challenge is unprecedented in speed and scale, but not in kind. We've faced climate shifts before. We've adapted before. We can adapt again, with wisdom, cooperation, and justice. The ice cores don't predict doom. They predict physics. And physics, while challenging, is knowable, predictable, and manageable. The real lesson of the ice cores isn't about temperature or CO2. It's about time. They record 800,000 years of Earth's history, a timescale that dwarfs human lifespans, civilizations, even species. This perspective is humbling. It reminds us that we are part of a much larger story, a story of planetary change, biological evolution, and human resilience. Our actions matter not because we're the center of the universe, but because we're participants in this story. We have the capacity to shape the next chapter, for better or worse. The ice cores have given us a glimpse of that chapter. Now it's up to us to write it wisely. So what is the final message of the ice cores? It's not doom. It's not denial. It's not even hope, though hope is part of it. It's agency. The agency to prepare. The agency to adapt. The agency to cooperate. The agency to act justly. The agency to shape our future rather than be shaped by it. This agency isn't granted by the ice cores. It's inherent in being human. But the ice cores clarify it. They show us the consequences of our choices. They give us foreknowledge to act wisely. They remind us that our actions matter, not because we control the climate, but because we influence our response to it. This is the gift of foreknowledge, not certainty, but clarity, not ease, but purpose, not escape, but engagement. The ice cores have spoken. They've told us what's coming. They've shown us the path. Now it's up to us to walk it, with courage, compassion, and collective resolve. The challenge is real, but so is our capacity to meet it. The ice has preserved the past. Now it's up to us to shape the future, not with fear, not with fatalism, but with agency, wisdom, and hope. The ice cores have given us the truth. What we do with it will define us.